A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. Kishan, the results have been good this time, and few of the expected candidates they have cleared and cleared with good ranks. The final list will be generated after verification of the entire list, but we have had a good result so far, as far as we have seen. Uh, Jigar will let you know. Okay, kindly write a mail to IS Live and you'll get an idea about it. So on 28th, I think we'll have the prelims discussion, live prelims discussion on YouTube in the evening. So uh, I don't know about the sessions or the class, the weekend class. Kindly send a mail and let us know, and we'll let you know. Shruti, the theory for the formation of Earth is referred to as accretion theory. ACCRETION, accretion theory, where things got together over a period of time. After collisions, things started getting together. Ashwant, it comes naturally. Confidence will come with your preparation. If the preparation is good enough, just don't target about whether you will achieve and what you will achieve after 1 year. Don't think about it. That is too much of pressure on yourself, and that gives rise to daydreaming and deviation also. What I would suggest to you is fix a short term target, right? And fix a long term target for that as well. So short term target, get an idea about it, that what will you study in 1 day, 1 week, 1 month, and stick to that. Keep chipping on that. All places names, the ones which are relevant for current affairs, they are important. Anjali, not all the places for distribution of volcanoes need to be remembered. Few of them, which are, let's say, the major ones which exhibit all different types, those are the ones. Around Pacific Ring of Fire, you should get an idea about a couple of them. Around the divergent boundaries, you should get an idea. And then the hotspots. That's it. Yes, if Mount Etna has erupted as it has for the past few days, just get an idea about where Mount Etna is and try to think about it, that why Mount Etna would erupt. What kind of conditions internally would have led to the eruption of Mount Etna? So, hello, a very warm good morning to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session of geomorphology, which probably is going to be the last session for geomorphology, where we are going to talk about landforms which are created by the exogenic forces or by the outside forces. So, when we talk about the entirety of the planet Earth, we have to understand that planet Earth has got simultaneously various forces acting upon it. Forces which are acting from the interior consistently. They lead to the movement of the land with respect to each other. That is where we have seen that Himalayas, they will be able to collide with the region, or rather the Indian plate will be able to collide with the Eurasian plate and leading to the formation of Himalayas. We have seen that how you have the formation of the Atlantic Ocean as the plates tend to move apart. So forces from the interior, they end up creating an impact on the surface, and they can also lead to a rise of a particular landmass. Maybe a landmass slowly and steadily starts rising up, and they can also start sinking down due to the convective current which is present in the interior. They can also give rise to sudden impacts and sudden forces such as earthquakes and volcanoes. Now, all these forces that we have talked about, they are acting from the interior of the planet, right? Heat which is emitted from the interior of the planet. And that heat has been present in the planet since the time of its formation itself. Now, those forces which are acting from the interior of the planet, those are referred to as endogenic forces. Whereas, when we take a look at the forces which act on the surface, for example, let's suppose you have an upraised hill which is created, and there's a strong wind which is moving. That wind will take away some of the portions of that upraised mountain. That is exogenic force. So that is what we are going to target today. We are going to study about the exogenic forces and how they end up shaping the landforms. So what is it that we had studied yesterday? Was basically yesterday we had delved deeper into what are volcanoes, what do we understand by volcanic eruptions, and also where is it that we experience volcanic eruptions, what are the various different kinds of it. We looked at various landforms and features such as calderas, and we also looked at certain features such as mantle plumes, hotspots, and that helped us understand how the interior of the planet behaves. Later on, we looked at the type of magma, the classification of magma based upon the chemical properties, that is based upon the presence of silica, which is present in the molten material. We can determine whether the material will flow easily or not. Then after that, we looked at how folding and faulting occurs. That is, how is it that a land gets crumpled into a kind of a fold or gets stretched to develop a fault or a crack. Now, today we are going to look at these exogenic forces that we have talked about, and there we shall gain an idea about the landforms created. For example, when a river drains down the mountain, it comes down with a very great speed. Now, there it ends up creating very deep valleys and gorges. But the same valleys and gorges will not be created, let's say, when the river is moving around the plains. Similar is the case with the glaciers. When the glaciers move, these are mighty masses of ice which are in motion. So they also induce a kind of a formation of a landform. So all those landforms we are going to study in significant detail from a visualistic approach. So that when you take a look at the visual, you will get an idea automatically, if you apply your logic, that how this could have been created. Okay, so that is the approach that we are going to follow. Now here, this is relevant both for your prelims as well as mains. So for your prelims, from this particular portion, you can expect questions regarding types of landform, erosional slash depositional, and also agent of nature, creating a landform. Then, after that, in the mains exam, you can expect questions to be appearing from the portion of, let's say, landforms created by river or glacial action. They are generally focused upon. And also, you can expect in the mains mass movement and weathering also. Even in mass movement, landslide is focused upon, and basically it is merged with a portion of Indian geography in general if you take a look at the previous year question. So that is where here we shall be introducing ourselves to what do we understand by landslide, and slowly and steadily as we move to Indian geography we shall be able to formulate an entire concept that, for example, why is it that the Himalayan region experiences more landslides as compared to the Western Ghat portion of India and so on. So that is where we are going to delve deeper upon. Okay. So without further ado, let us initiate the discussion. So, first of all, let us understand the very basics of landform development or creation of a landform. Now, any landform that you observe on the planet surface, that landform is a byproduct, is a sum product of multiple different forces. Continuously, you have both the action or the creation of endogenic forces, the impact will be observed, and simultaneously you will also have the impact of the exogenic forces. So broadly, the movement across the planet Earth, excuse me, so broadly, any movement that we observe across planet Earth, that is created either due to forces acting from the interior of the Earth or forces acting on the surface, the exterior of the planet. So the forces acting from the interior, that is referred to as endogenic forces. Okay, forces acting from the interior, and this will be forces acting on the surface. Kritika, in this case, I would suggest to you try attending. If this is your first session, this is one of those topics where you don't require that much of a brief background about the rest of the geomorphology. Try attending it from today onwards. Slowly and steadily, the concepts will get cleared. Okay. So, for example, after this, we are going to initiate a new module for discussion. So, that is where you won't find much of a decoupling there. So, try to grasp it. If not, recorded videos are available. So, here, when we talk about these exogenic forces, these are the forces acting on the surface. Now, how is it that the forces act on the surface? Or which forces are the ones which act on the surface? So, for example, let's suppose you have the existence or a creation of a mountain or a hill. Now, that hill would be created primarily due to any force which is acting from the interior. Let's say the land has been raised up, the land has been, let's say, folded up, or something like that. But this hill will experience wind movement, this will experience rainfall. As a result of that, what will happen? As a result of that, this starts getting eroded, taken away by the wind, carried away by the water, and slowly and steadily its height starts to decrease. Okay, And this water, etc., everything, they will carry the portion of that mountain or the hill, they will drop it somewhere in some other part of the land. They will, let's say, drop these eroded materials. So that is why the forces acting from the exterior, that is the exogenic forces, these are also what are referred to as levelers. That the forces from inside, they can create various indentions on the ground. They can raise a hill, they can raise a mountain, they can create a plateau, they can create any landform. But from the outside, every force will try to level it off. Anywhere, wherever you have a slightest amount of, let's say, protrusion in the land, as the wind blows, or if a river blows from this region or moves from this region, it will flatten it out, it will erode it out. So that is why they are referred to as levelers. Every point of time, both endogenic and exogenic forces, they keep on acting simultaneously. It is not going to happen, or it is not going to be the case that first endogenic forces will act. When their work is done, they will report to the supervisor, and then only exogenic forces will start acting. No, they continue to act simultaneously. For example, let's suppose, take the case of Aravalis. We refer to the Aravalis today as hills. Now, these Aravalis in the region of Rajasthan, their height is not very significant. It is around 800, 900 meters in certain cases, and in many cases, even less than that, around 100 meters, 150 meters, or so on. Now, in this situation, when we talk about the Aravalis, at one point of time, these mountains were very, very tall. It is said that they were so very large, so very tall, that you had ice moving down the mountains, you had glaciers moving down the mountains, feeding very large rivers. But look at the mountain today. So, there, how is it that the mountain's size has reduced? So, once the internal forces leading to the rise of the mountains, once that came to a stop, the external forces, they were the predominant one. Before that, as the mountains were getting created, both the forces were acting. And once the internal forces came to a stop, the external forces dominated and the height started to reduce. For example, take the case of, for example, the Himalayas, the Himalayan mountain chain. Now, these Himalayan mountain chains, they are consistently being elevated in terms of their height. Consistently, the height is increasing. Why? Because the Indian landmass is crushing into the Eurasian landmass and the land is getting folded. So, as the folding is happening due to crushing, the height keeps on increasing. But simultaneously, the wind action continues to chip away and take away some or the other part of the rock. Now imagine one final day when the Himalayas, their height will stop increasing because of the forces from interior. It is those external forces which will be the only force which will act, and that will create a level land. So erosion and weathering will keep on happening as long as the land is leveled to the region around sea level. Okay, till that point of time, there will be some or the other erosion or weathering which will keep on happening. So that is the exogenic force. Exogenic forces, they are initiated due to maybe temperature conditions, climatic conditions, or other geographical conditions such as river movement, glacier movement, etc. Right? Now, here, when we talk about the endogenic forces, these endogenic forces are further subdivided into sudden forces and diastrophic forces. Sudden forces which act all of a sudden, and diastrophic forces, these are very slow acting forces. Very slow acting forces. Very slow acting forces. And there, these slow acting forces lead to, let's say mountain formation, rising of land, subsidence of land, etc. We'll take a look at it, because even this diastrophic forces is divided into further two types. We have studied all of them already. So today we shall be concentrating upon the exogenic forces. So here, if you take a look at it, then what is diastrophism? Diastrophism is a slow acting force which is going to lead to the process of deformation that changes the earth's surface. So if you have the land mass, let's suppose that land mass can experience compression, can experience expansion, tension, or can move with respect to each other as well. So that all of that is included into diastrophism. This diastrophism is further subdivided into two types of forces, that is epeirogenic and orogenic. Epeirogenic basically means that, let's suppose, if there is a landmass, due to heat present from the interior, let's suppose the landmass in this region slowly and steadily starts to rise. Let's suppose they start to rise ever so slowly. That is an epeirogenic. Right? So they will rise up, the landmass even sinks down in certain cases. That is what is referred to as epeirogenic. And when we talk about orogenic, orogenic, whenever you come across the term orogeny, orography, anything in terms of geography, that is associated with mountain or anything associated with a mountain. So orogenic forces, they are the mountain forming forces that can lead to the formation of a mountain. So for example, folding can happen, leading to formation of a mountain like Himalayas. For example, a crack can push up the land above the ground, leading to formation of certain hills such as the Vindhyas. So that is how mountain building also happens. So all these are a part of diastrophism. These are the slow acting forces. Okay? These are slow acting forces which lead to vertical and horizontal movement of land. Okay? So that is basically diastrophism. Now, simultaneously, whenever you have an endogenic force which is acting, or wherever, at all point of time, you have the consistent action of exogenic forces as well. Exogenic forces, again, to repeat it, forces acting from the interior. That is what is exogenic force. Now, here, when we talk about an exogenic force, so it can be a wind movement, it can be rainwater, it can be river movement, and so on. Or rather, when we say exogenic forces refer to, pardon me for that, forces acting from the surface. So I have a couple of questions before that. How both vertical and horizontal? That it is that question which distracted me here. So how both vertical and horizontal? Okay. Do you think at a point of time the land will go upwards also and sideways also? Can that happen? So basically, we have already seen that you have the creation of, let's say, or the existence of a convection current which can drag the land away from each other. There can be a horizontal movement. Horizontal movement we have seen where? In the case of plate tectonics. Have we not seen that? Horizontal where we have seen? In the case of plate tectonics or plate movement. So whenever you have two plates coming with respect to each other, coming towards with respect to each other, moving away with respect to each other, moving parallel to each other, that is a horizontal movement or not? And whenever, let's say, we have a condition where due to a convection current in the interior, the land gets forced up or forced down, what is that kind of a movement? Is it a vertical movement or not? So both of these will be acting, but at the same time, will they be acting at the same place? Depends on that region. Okay, if for example here you talk about, so here there will be some upheaval and there will be some movement away in a horizontal manner. So that is a kind of a diastrophism. Any force acting from the interior, the slow acting force, can be categorized under diastrophism. Right? Diastrophism can lead to the movement of the land, evolution of the land. All this we have already studied. Don't think of it that this is a new concept that you are being introduced to. This is a portion that we have already studied significantly prior to today. So diastrophism is only due to endogenic forces? Yes. Diastrophism refers to the process of deformation acting from the interior. That is basically diastrophism. Okay, it can lead to a rise, uplift, or sinking of the land, what is referred to as eperogenic force, or it can lead to folding and faulting, what is referred to as an orographic force. Okay, Shelly, is that understood? Is the mountain forming force not a vertical uplift force? No. Mountain is formed if, let's suppose, the land is crushed and there is folding. If this land, how is it that a fold mountain is formed? When both these are compressed, it can lead to a formation of a fold mountain here. If even in the case of block mountain, you can have the faulting, which can lead to the formation of a block mountain. But when we talk about, let's say, the conditions of a region, let's say a vertical uplift or vertical subsidence, so there you have a land simply raising up and sinking down. That is the vertical uplift and sinking down. Okay. Sudden force is force which acts all of a sudden. That is what is referred to as a sudden force. Okay. Okay, how many of us we are absolutely out of our places by hearing the term eperogenic? It is basically, I guess, the term which has perturbed many of you, that what is this particular term, what is eperogenic, and basically when you come across such a new term, that puts you off your grid. Plateau is see, it is a flat table land, it is not a level land. Okay, listen to this very, very carefully. I am going to ask about, or I'm going to explain it one final time. Listen to this very carefully. When we talk about the planet Earth in itself, leave this slide. When we talk about the planet is acted upon by forces acting from the interior. Now, these forces acting from the interior, why are they initiated? They are initiated because there is a lot of heat trapped in the interior of the planet. And that heat is what is referred to as residual heat, which has been trapped ever since the formation of the planet. Now, when you have a lot of heat which is trapped in the interior of the planet, now that heat is emitted time and time again. Sometimes what happens is, let's suppose this is the surface. Now, sometimes when that heat is emitted, let's say from the interior, it reaches the crustal portion and diverges. Now, when this happens, the land gets pulled or pushed away from each other. Okay. Now, when the land is, let's say, getting pulled away from each other, it will develop a large crack, right? Because the land is getting pulled away from each other. It will develop a large crack, it will break. So, when the land breaks and there is movement, that is what is referred to as faulting. Now, as this land is moving in this direction, let's suppose there is already a particular landmass in this area. So this particular land will be colliding with the earlier landmass. There will be convergence. A portion of that crust will get folded, and you will have the formation of a kind of a fold mountain, like Alps, like Urals, like Himalayas. You will have the formation of a fold mountain. That is what is referred to as folding. Both of these are a part of orogenic forces. Now, the forces are acting from the interior of the planet. Sometimes what also happens is that you will experience or you will come across a situation where the heat rises up, hits the land, and then there's a divergence like this. Now, in this situation, what will happen? Slowly and steadily, this land starts rising up. Slowly and steadily, that land will rise up. As that heat continues, maybe after some point of time, and you have a vertical rising section of heat from the interior, this will start to push the landmass up ever so slightly. So over a period of time, this entire region might get uplifted. Okay, so that is where you have a vertical uplift. This is vertical uplift. Now, this is different from folding, by the way. Now, here, when you have the convection current, this convection current in the interior generally ends up behaving like this on both ends. That is how convection currents generally work anywhere and everywhere. Now, wherever you have the downward component of the convection current which is sinking, it will try to pull the land down here. It will try to pull the land down in this region. And that creates a kind of a depressed area in many of the cases. And this is a vertical downlift or a vertical downward motion. Now, both of these, vertical uplift and downlift, they are not a part of folding or faulting. These are acting in a slow manner, and these are referred to as aperogenic. Aperogenic and orogenic taken together, they are referred to as diastrophic forces. That is what we have as diastrophic forces. Okay, so this is the internal functioning or the forces acting from the interior. Is that understood? Convection current we have already seen earlier. Convection is the transfer of heat from any particular region in the interior to the region on the exterior. For example, when you boil water, when you boil milk, it is, how is it heated? By the movement of water. So that is what generates a convection current. That is present in the mantle also, as the heat is transferred from the lower region of the mantle to the outer region of the mantle. Intensity of convection is absolutely different in different parts. That is correct. Okay, so that is basically your endogenic forces. Now we come to the exogenic forces, or the forces which are acting from the exterior, from the outside. Now, when the forces are acting from the outside, they can happen or they can lead to certain kinds of outcomes: weathering, mass movement, erosion, and deposition. Let us take a look at each one of them, what they are. Okay, and let us try to understand that how they are created or what these forces are, where do they act. So we start first of all with weathering. What do we understand by weathering, and why it happens, where it happens? So when we talk about, let's say, weathering, it is an English terminology also. It is used in your normal English communication and English vocabulary also. So how is it that weathering results in, or how is it that it happens, or what is it first of all? So answering the what, how, and why of it. So starting with the what. So whenever you have a large rock or any particular rocky area, now that rock in its own place starts to disintegrate under the influence of forces like temperature, wind, river or rainwater, biological events or biological agents of nature, for example, maybe plants, maybe burrowing animals like rats and rodents, maybe by a chemical action where rainwater dissolves certain materials which are present in the rock. So it is a disintegration of the rock in its own place owing to the external factors. A rock which is placed on the ground, a large rock, let's suppose, it eventually breaks down into some smaller portions. It breaks down into some smaller portions. These smaller portions will be or broken down into sub smaller areas and sub smaller portions. Now, why will it get broken down? Where will it get broken down? So it will get broken down wherever you have those weak points on the rocks. And why? When it is exposed to physical agents of nature. That is heating. Heating of anything leads to expansion. Cooling of any material leads to contraction. Think about a large rock. Imagine that when it is heated significantly for many, many years in a region, slowly and steadily expanded, cooled during the night or during the winter season. So a large rock consistently expanding and contracting, will it weaken the joints and the structure of the rock or not? It will. The rocks will get weakened at the various different structural joints. And when it gets weakened, it will simply crack, break off into many smaller subparts. It is eventually, that is how that we observe the formation of soil. Even the soil formation that we see is because of this process itself. That all these rocks, they continue to get broken into smaller and smaller and smaller particles till you have the formation of these soil, minute soil particles. So here, the rock need not be carried to any other place to get broken. Wherever the rock is present, there itself, it will get broken by the outside agents. That is weathering. Weathering is of three types, right? Let us take a look at the definition of it. Action of climate and weather, animals and plants on the land surfaces to break down a particular piece of rock physically, chemically, or biologically. That is what is weathering. Now it is of three types. And this classification is done based upon which is the predominant factor which has initiated the breaking down of the rocks. So let us take the case of physical weathering, for example. And by the way, what do you think? Your normal logic, what does it tell you? This entire process of breaking down of the rocks, is it something which will happen in a short time period, or is it something which will take a very long time period? What do you think? Perfect. It takes a very long time period. Generally, the formation of these, they take a very long time period. Okay? It is a very slow process. A large rock which can expand for a few hundred meters, maybe, it might take around 1,000 years and thousands of years for that to be disintegrated into many small parts. So it is a very, very slow process. So here, let us understand each one of them. Physical weathering. In this, the physical agents and the physical action on the rocks, they are predominant in the breakage of the rocks. Let us see how. So suppose you have a particular rock, let's suppose. Now, let's say there is significant amount of heating during the summer season when the temperatures are very high. Let's suppose this rock is present somewhere to the north of in the region, let's say in Iran. Why I have taken the example of Iran here is, or any particular region in that area, is because during the summer months the temperature can be 46, 47, 48 degrees. During the winter months the temperature will be very, very minimal, around 0 degrees also the temperature reaches. Now, during the summer months, let's say that when the temperature has increased, there will be ever so slight expansion in the volume of the rocks, ever so slight expansion. During the winter months, there is significant amount of cold conditions, so the rocks will try to contract ever so slightly. Again, next summer, it will expand. Again, next winter, it will contract. This continues to happen, expansion and contraction. And a repeated expansion and contraction, it weakens the rocks. And that is where maybe a crack tends to develop. Let's say a crack has developed. Now, let's suppose in this crack, which is a few meters deep, during the rainfall or the rainy season, let's suppose water has penetrated inwards. There is rainfall and water has come inwards during the rainy season. Now the winter temperature is very, very low. And in winter, this water which has fallen in, that water will be frozen to ice. When water gets converted to ice, do you think there is contraction which happens? Volume remains the same, or do you think there is an expansion which happens when water gets converted to ice? Good. Beautiful. You have an expansion which happens, right? Water getting converted to ice always leads to a kind of an expansion in the process. Now, here, water is already present in the crack. And now, that water is getting converted into ice, means that water will tend to expand ever so slightly. So, when it tries to expand, what will happen to the crack? The crack will feel a pressure. The crack will also expand. It will further develop. A repetition of this process again during the summer months, everything will melt. And there may be more rainfall, more water. Again, during next winter, that water will freeze. Slowly and steadily, this crack that deepens, it might puncture the weaker areas. Simultaneously, expansion, contraction is also happening. And eventually, if the crack deepens enough, let's say over a period of 200 years, 300 years, what will happen to this large rock? It will get broken. It will get broken into two. That is weathering, right? So that is what we refer to as weathering. Now, and here, that is what is referred to as physical weathering. Now, let us talk about biological weathering for a bit. And for biological weathering, I will take you back to the creation of a crack itself. Okay. In summer, it will expand. In summer, the rock will expand because there is significant amount of heating. That is why it will be expanding in summer. Any substance will expand in summer. It will contract in the winter. Due to cooling, it will contract. So I knew this will be the case. Many of us, we have a doubt about the water and ice thing. So guys, this is Science 101. When you talk about water, water is the only liquid, when it solidifies, it tends to expand. So that is why the density of water, the closeness of materials is maximum at 4 degrees Celsius. If you cool water below that temperature, it will expand. Ice is an expanded form of liquid water. All those of you who think that there is a kind of a miscommunication going on or a slip of tongue going on, it is not. Because in the case of liquid water, why is it that ice occupies a greater volume? Is very simple. Ice is a crystal form of a solid where the molecules, they end up forming a kind of crystals, and those crystals will occupy a larger space as compared to the liquid H2O, which doesn't have crystal format. So that is why in order to form that crystal, it will occupy a larger volume. Try it out at your house today. Okay, fill a particular ice tray to a level, mark that level where you have filled the water, let it freeze. After getting frozen up, you will realize that ice occupies greater amount of volume. Always understand that ice will occupy much larger volume as compared to water. So all those who had this question, I hope that is solved, it is understood. Okay, water is an exception as compared to the other liquids. In the case of other liquids, freezing means contraction, melting means expansion. It is only in the case of water where this exception stands, because water forms a kind of a crystal. Okay, is that understood? Okay. Now let's come to the biological factor of weathering. Now here, suppose when we talk about this heating cooling which was happening, let's suppose a crack has developed, and biological weathering you guys would also have observed in your day-to-day lives. It is very easy to observe. Now here, let's suppose, because many of the times when you walk down out in the nature, if you do like to walk in the nature, if you do like to explore, let's say, natural landscapes, you would have observed in many of the areas you have the rocks, and the rock might be absolutely barren, and in between you will observe that one or the other plant would be growing through a crack here and there, right? Eventually, that is what will lead to biological weathering in the long term. Let us see how. So, here, when we talk about it, let's suppose there's a crack and there's a plant which starts growing from here. Now, this plant will have its roots as well. These roots will spread extensively along the cracks. Why? Because that is where they are getting all their nutrients required. But slowly and steadily, as the plant is in existence here, few animals will also come in. Animals, not in the sense lions and tigers, but few of the smaller ones like rodents, rats, few of the insects will come in. Maybe they will bring in another seed of another plant here. So you might have another plant which starts growing here. Another plant starts growing here. Because here in the rocks, you will have plenty of nutrients. So slowly and steadily, as the roots will expand, these cracks, they will start widening. For example, if ever you have been to any of those government bungalows or the government houses which are present, right, the older ones, the ones generally used by the railways, no offense meant to anyone. So the ones generally used by the railways, the railway bungalows that you have, which is given to the DRMs and so on. Now, in all those, you will find that around the walls, the sides of the walls, there is a growth of small plant here and there. How is it that the plant is growing on the walls? It is because they get the nutrients in the various different areas. And that is how they start to grow. And when they start to grow, slowly and steadily, you will see that the walls, they start to weaken. The cracks develop, the outside plaster of the wall, that starts to fall as the plants are growing. Why? Because the roots, they try to enter into deeper areas, and that weakens the entire structure of the wall, right? Leave it for 5 years, 10 years, and 15 years, maybe after some time when you come back. And that is the case in any area of the country where you have a lot of, let's say, government services and a lot of government jobs and those government employment areas. You'll find that in the older houses, which have been left abandoned, let's say for 5 years, 10 years, you'll find that one or the other wall has come down and now the plants dominate in that area. So that is because they have weakened it. They have weakened this entire structure, developed cracks, and everything comes tumbling down. So that is how slowly and steadily, as the plants will grow, rats, mice, they will also come in. Now, these are burrowing animals. They will start to build burrows here. That will further deepen the crack. Eventually, what happens? The rocky portion gets broken off. So that is how you have the weathering, which is happening due to biological events. And that is biological weathering. Okay. So this is the example of biological weathering. Now let us take the example of physical or chemical weathering. So how is it that chemical weathering happens and where is it that it happens? So let's suppose you have a particular rock type. And let's suppose this particular rock consists of calcium, significant portion of calcium here in this area. Now, when we say calcium, calcium is soluble in water. It gets dissolved in water and can be carried out by water as a solution. Now, in this area, there is significant amount of rainfall, expansion, contraction, everything which is happening in the rock. Okay? Right? Everything is happening here. Over a period of time, let's say there is a development of a crack. A crack develops. Now, when a crack develops, now rainwater will be able to enter and gets in touch or contact with calcium. Now, when it gets in contact with calcium, it will start dissolving it. But it has got no other place to go. Next season, maybe, or next year, or maybe next decade, when the crack deepens, more water will get in. More water gets in this area. It will dissolve more calcium. Calcium will be easily soluble. Slowly and steadily, calcium from all the surrounding areas, they will start to get dissolved. The water gets deeper by dissolving more and more calcium, more and more rainfall happens. Eventually, what happens? All the portions where the calcium was present, water will continue to dissolve it slowly and steadily as the level of water is provided by eventual rainfalls. And thereby, because that calcium was forming the internal structure of the rock, now that calcium has been dissolved away, means what? The rock is free to be broken. The rock is free to be disintegrated. Now, an example of this, let me tell you. For suppose, many of the times, when let's say, I'm not talking about the normal roads here, but I'm sure many of you would have come across in your day to day lives while you are moving around or in your city, in your village, in your vicinity, you might have some or the other rocky area here and there. Now, sometimes when there is a heavy rainfall, you would find that from the region where there are rocks, if they are present at an uphill, you have a whitish, water turns slightly whitish, and there's a lot of foam which develops as well as the water starts trickling down these rocks. You would have observed it during the peak of the rainy season. Now, that is basically water trying to dissolve something, getting some portion dissolved, and then draining away. So over a period of time, repeatedly, so immediately after the rains they stop, you might not even be able to spot any difference there. But over a large period of time, years, decades, centuries, that is how larger rocks are broken and disintegrated into many smaller parts. That is what we refer to as chemical weathering. Now, in the case of chemical weathering, those rocks will be impacted which are soluble in water, right? So, not the rocks entirely will be soluble in water, but those rocks which consist of, let's say, any element, any compound which is soluble in water, those rocks will be impacted quite significantly. So, that is why generally calcium and those particular rocks consisting of calcium, they are the easiest prey. That is why in calcium bearing rocks, you'll find that the rainwater ends up carving very deep caves, very extensive caves, because the water keeps on dissolving calcium as it ends up moving ahead. Now, here, when you think about it, what do you think? Out there in the nature, do you think physical, chemical, and biological weathering, all of that will be acting independently, separately, at different point of time? Or will it act at the same time? So let me tell you, out there in the nature, all these events, perfect, all these events, they act at the same time. It is not going to happen that at some place only the physics department has taken it up, so physical weathering will happen, chemical weathering will happen, and somewhere else biological weathering. No. When you have a rock out there in the open, there is a development of a crack, physical weathering. There is some materials which are dissolved, chemical weathering. Out of those dissolved materials, maybe you have a plant growth and biological weathering. So simultaneously, all these forces, they keep on acting and they lead to the breakage of the rocks. Okay. Now, after this, we come to the portion of mass wasting. So please don't get waylaid by the term wasting, because when we think about waste, we think about something which is thrown away. So don't think about this wasting as a typical aspect like that. So mass wasting here refers to mass movement. Okay, this refers to mass movement. Mass movement of what? Of materials, of disintegrated materials. Okay, I have sir, rocks with chemicals are only experiencing chemical weathering. Not necessarily. Rocks with chemicals, what do you mean by rocks with chemicals? Do you foresee a situation where inside a rock there will be concentrated sulfuric acid, or there will be hydrochloric acid, sulfuric, and nitric acid present and trapped within the rocks, and they will have all the chemical battles within them? No. When we say chemical weathering, the materials which are present, they interact with the water and they are water soluble. That is how they are able to maybe drain themselves out. And Prashansa, example of physical weathering: expansion, contraction of the rocks weakens the structure, cracks the rocks, breaks them apart. So, Alok, is that understood, my dear friend? Okay. All the rocks have different or some or the other minerals which are present. Some minerals are soluble in water, some minerals are not soluble in water. So, for example, gold is not soluble in water, calcium soluble in water, sodium sometimes soluble in water. So, depends upon what kind of material is present, accordingly, it is drained away. So, here, let's come to the mass movement. When we talk about mass movement, so mass movement of what? Of materials which are free to move. So if, let's say, we talk about a land like this, a region like this, you have a lot of loose soil which is present here. Loose soil means not bounded by a plant or not held somewhere. It is free, the loose soil that you see side of the roads, etc. Now here you have a lot of loose soil. Now on its own, will there be any movement on this flat land? No. Let's suppose there's a lot of rainfall here, but the land is absolutely flat. So water might accumulate, Muddy region might be created, but will this flow? No. Will this move? Absolutely not. But imagine a landscape like this. And here, let's imagine you have a lot of these loose soil, which is present. Now here, when you have a lot of this loose soil which is present, if there is rainfall in this region, what will happen now? Now you have soil which is free to move, you have availability of water, and there is gravity after all which is acting as well. So that is where all of these materials will tend to move down in significant quantity. A mass of material will move down in significant quantity. And that is what is referred to as mass wasting or mass movement. So, anywhere, wherever this mass movement is happening or will happen, you will invariably find that the land has got to have a kind of a slope. Slope might be very steep, slope might be very gradual, but the slope is essential, right? So, anywhere where there is a slope, there will be influence of gravity, and that influence of gravity will pull the materials down. That is basically one of the features here of mass wasting or mass movement. Influence of gravity is paramount in this case. Okay. Now, this mass movement or mass wasting can happen in a very quick manner. It can also happen in a very slow fashion. It is dependent and it is contributed to various other forces. Let us understand that. Various other factors, rather. Let us understand that. Now, suppose you have a particular region with a slope like this, right? And a region with a slope somewhat like this. Now, here, if you have loose soil, in between, let's say you have few boulders as well, impregnated with boulders and rocks. Boulders are shorter forms of large rocks, the ones that you see sometimes when you're walking up the hill or a mountain. You will see sometimes lying on the sides of it, not a large rock but a smaller one, that is a boulder. So here, let's suppose lot of loose soil. Here also, let's suppose lot of loose soil is present. Now if it starts to rain here, okay, all these materials, they will get dissolved in water, or rather they will get mixed with water. Not exactly dissolved, but they will get mixed with water, form a kind of a liquidy, muddy kind of a substance, will initiate a movement down. In this situation, in the second situation, it does not require that much of water to flow. Even the slightest amount of water can initiate a movement downwards. Now, out of first case and second case, let's suppose both of them are driven by rainfall. Out of the first case, let's consider this A and let's consider this B. Okay, I'll launch a poll, let me know. Out of A and B, in which of them do you think the movement will be much faster? Movement will be much faster out of A and B. In which of them? What do you think? It is very apparent by the figure itself. And that gives us an idea about what drives the forces. Very good. So here, the movement will be faster in this case of B. Why? Because the component of the gravitational force will be much higher, because the slope is going to be much steeper. So it will all come crashing down very significantly. So slope is a significant factor in determining whether an object will move or the mass movement will happen in a very quick pace or in a very slow pace. Now, let me give you another scenario. Let us talk about another scenario here. So here, if I have a slope like this, steepness means what is the gradient of it. Whether it is, if a slope is steep, means the angle is very high. If the slope is gradual, means the angle is very low. Now here, let us consider two places, two different areas. Now in one of these regions, both of them, let's suppose, has got loose soil. In one of these regions, you have a lot of this loose soil, right? Now here also slope is there. So sometimes the movement will be initiated like this itself. Slow and steady movement of soil down the hill, down slope. And we observe this in almost all the major areas or habitations. Wherever the land has got a certain amount of slope, you would have observed, even in your region, if the land has a slope, you would have observed that the telephone poles, they end up bending in one direction, all the telephone poles. I'm not talking about those old government telephone poles, or the old installed ones which are almost fallen to the ground. No, that is because of poor repair. I'm talking about the ones which are still functioning, and they are indicating a slight amount of bend in the same direction. Sometimes, while you are, let's say, moving across a slight hilly area or a slight slope, not a steep slope, you would have observed that in many of the cases, even the boundary pillars installed by many ones or many individuals in their backyard, even those boundary pillars exhibit a slight amount of angle. So all of that is because the soil underneath is moving, and it is moving very slowly. It is moving so slowly that we are not able to look at it and experience it on a day-to-day life. But the impact is something which is visible, let's say 5 months, 1 year, 5 years down the line. The speed of movement is slow. So the speed of movement can be fast, can be slow. In the same region, let's suppose there is occurrence of high amount of rainfall. Now suddenly the speed of movement will be fast, right? So here water content also in a way initiates and determines what will be the movement, how much will be the movement, whether it will be fast, whether it will be slow. When there is a lot of water, movement is very fast, significantly faster. And then you have the condition of volume of materials. Volume of materials which can flow down the slope. Volume of materials means the availability of loose substances which are ready to flow down the slope. Substances such as sediments, loose soil, rock boulders, etc., which are ready to come down the slope, that is exhibited by the volume of material here. So here, let's suppose you have no loose soil, right? You have the presence of only trees, small plants, etc. Then not a lot of volume of material is available. So as the water drains down the slope, maybe due to excess rainfall, it will carry small pieces of soil here and there from the sides. But if, let's say, there is a lot of loose soil, everything will be carried down the slope. So all the mass movement that we come across, that is dependent upon these major conditions. Another condition, for example, if we consider another condition, let's suppose the slope is somewhat like this. Vertical. Now, if you have loose materials here, loose materials which are present here, they don't require water to come down. They don't, or they are not even concerned with anything else. This will simply start falling. So this kind of a mass movement That is what is referred to as a fall. You have rock fall, you have debris fall. This is a fall where it is vertical. Everything will start falling, right? When you have down a slope, materials in the availability of water will start moving very fast. That is what is referred to as a slide. Slide means you have a slope and you have, let's say, significant portion of land which also comes down with the availability of water. Landslide. Okay. Then these are basically the types of your mass movement. Let's take the example of these. So when we take the example of these here, this represents what is a landslide. This represents what is referred to as a creep, and the bottom figure represents what is solifluction. Let us understand that. Landslide. If you can look at the first image, here you will get traces of humongous availability of water. This is water flow. And a lot of substances, they have come crashing down the mountain. So this landslide, it will always end up exhibiting a kind of a fast movement. Fast movement. You do need to have a kind of a significant slope. So steep slope. Availability of water is absolutely required, because that water will take in the soil as it continues to drain down the slope. So water availability is required. Water availability is required. Then after that, eventually, you do need to have a lot of loose materials. In order to move along with water, you need to have loose soil, right? You need to have loose rocks that are taken by the water. So availability of materials, volume of materials, loose soil and rocks. Okay, that also needs to be available, right? So that is a kind of a mass movement which is initiated by all these events. So this is basically what is referred to as landslide. Okay. Jeho, can I download this class? Hmm. Along with all the participants, also you want to download, or you want to download only the one who is speaking and the video? So clarify. In either cases, it cannot. I think it cannot be downloaded. I hope it is. It cannot be downloaded. So that is basically what is landslide. And then we have creep. Creep is basically a very slow movement. Now, in this slow move, wherever you have a slow movement, what is it that we can extract from here? Slope will be very gentle, because if the slope would have been steep, materials would have come down almost immediately. So slope is very gentle. Is it? It can be downloaded as well. Okay, good that you informed me about that. So it has got a very gentle slope here. That means it is able to move very, very slowly. Then, if the water would have been available in significant proportion, that water could carry significant amount of that soil. But here, if it is moving slowly, that means availability of water would be less. So here, water availability is less. Is very less. Then volume of material to move is also less. Okay? So that is what is a creep, a slow movement, a slow mass movement. Observe how, in a particular region, I'm sure many of you would have come across this scene or the scenario where, let's say, the fencing of a particular building or a particular boundary, all of them indicate a tilt in the same direction. That always indicates that it moves. The soil underneath is moving ever so slowly. Then you have a unique case. That is why I've taken the example of this, of what is referred to as solifluction. Now, what is this solifluction? So here, observe this image first. Here, if you will observe, it appears as if the topsoil is moving like a liquid, isn't it? That appearance comes as if it is moving, draining down like a paste or a liquid. So this happens in very high altitude areas or very high latitude areas closer to the polar region, where the temperature is so low that the bottom soil is permanently frozen. The condition is referred to as permafrost, permanently frozen, permafrost. So in those areas. So what happens? So first of all, observed in regions of permafrost. Now, during the summer in those regions closer to the poles, for example, Greenland, summer in Greenland is not similar to summer in India. Summer in India means Delhi is roasting at 46, 47 degrees Celsius. But there, when you have summer, it is around 3, 4 degrees Celsius. Even during the summer, the bottom region is frozen. The top portion melts. The top portion's snow starts to melt. Now, when the top portion snow, the topsoil snow, that snow cover starts to melt while the bottom portion is still frozen. Can we say that the topsoil gets disjointed or disconnected with the bottom soil? Because the bottom soil continues to remain frozen throughout the year. During the summer, only the top layer of snow will get melted down, right? Where the bottom region is still frozen. So, can we think about it that here, slowly, as the top portion melts, it gets disconnected with the bottom soil? It does. And when it gets disconnected with the bottom layer of soil, let's suppose there is all that snow which has melted out, or if there is any amount of rainfall, all that soil will start flowing like a liquid. And that is what is referred to as solifluction. So solifluction is observed in regions of permafrost, that is very high latitudes, high latitude. Here you will observe what bottom layer is permanently frozen. During the summer, top layers melt, soil layers get disjointed or disconnected, and they initiate a flow. A flow in availability of water. Okay, that is the case of solifluction, because the bottom layer is still frozen, the top layer It is not frozen, it is free from ice. So here, imagine that you have the bottom layer as a deep solid, and the top layer is basically now free to move over the bottom layer. So if you have moisture or rainfall on the top layer, it basically starts sliding over like a liquid. Bottom layer cannot slide, bottom layer cannot move. Why? Because it is frozen solid. Why is it frozen solid? Because it is at very low temperature. So generally, across the coastal areas of northern Europe, coastal areas of northern Canada, and the coastal areas of Greenland, that is where you come across these events of solifluction. Now here, this is basically about the landslide. Ashwant, sometimes in very high altitude also you can observe this. This is the aspect of landslides. So it is the defined as a movement of a mass of rock, debris, or earth down the slope. It can be initiated in slopes already on the verge of movement by rainfall, snow melt, changes in water level, stream erosion. Stream can be the seasonal flow, it can be any river that is a stream. Changes in groundwater, earthquake, volcanic activities, anything can initiate that motion, that initiate that kind of movement. That is basically what is referred to as a landslide. Now, here, whenever you also have the shaking of the ground surface, there also the materials are significantly loosened. The materials become loose and they tend to move. There is an initiation of a landslide there also. So, whenever you have the kind of, let's say, an earthquake in mountainous areas, Himalayan regions, or in typical Western Himalayas or Eastern Himalayas, that can always initiate a kind of a landslide. More about the Himalayan landslide and landslide in other parts of India, we'll talk about it when we come to Indian geography. There is an anthropogenic factor. For example, let's suppose in a particular region, let's suppose you have dug out the slope. The slope is like this, you have dug it out, and you have constructed a road here. So the slope has become unstable now. So now you have a lot of loose materials which can drain down. So human activities are also always involved. Okay. Can this loss of topper soil or topsoil and rocks due to landslide lead to loss of fertility? Obviously, when the topsoil is taken away, fertility is the least of your concerns. You have a lot of people who will lose their lives. Okay. Creep is basically a very slow movement. A slow movement which happens, a slow movement which is initiated when you have a very gentle slope. So the soil very slowly ends up moving in, let's say, a speed of 1 centimeter every month or a speed of half a centimeter every month. That is basically what is referred to as creep. How soil layer gets disconnected, that is what I explained again, Lakshmi, looking at your question. Okay, I will explain it again. Think about it. In a region of very high latitude, when you have very low temperature, high latitude, I hope we understand high latitude, closer to the region of the poles. So think about it, in a region very close to the poles, when you have very low temperature, everything gets frozen. The bottom region of the soil, the top region of the soil, everything gets frozen. So if this is the soil layer, this is the bottom portion, let's suppose this is the soil profile, everything will be frozen entirely during the winter season. During the summer season, there will be slight amount of temperature around 3 to 4 degrees Celsius, and that is where the top portion might melt. So let's suppose here you come across the top portion which has melted out, but the bottom portion is still frozen. Now this is where you will have the presence of what? Loose soil. And it is all the while, it is down a slope, by the way. It is a sloping area that we are referring to. So all this is what? It is loose soil. This is the frozen portion of the bottom soil. Now, if there is availability of rainfall, now won't the top soil or the loose soil move over the region of the bottom soil? Or will the bottom soil also be carried? Obviously, the top soil will be carried. So that is where you say that it is solifluction. That is where we say top and the bottom layer gets disconnected. Is that understood? Is that understood or not? Please confirm. If you have a doubt, you want me to repeat, after that, kindly confirm, is it understood or not? Lakshmi, is that understood? I'm repeating the question again. Okay, do confirm it once it is understood. Then after that, we come across the portion of gradation. So when we talk about gradation, gradation is a kind of a leveling exercise. It is a kind of a leveling exercise where, let's suppose, in a particular region, let us assume you have an uphill area, and in a particular region, let's suppose you have a region of depression, right? Now, when we say gradation, that means from a particular region, let's say by agent of nature like a river, the materials are carried away. The river erodes them. The river, let's suppose the river is flowing from here, the river is eroding them. And it is carrying them over large distances and is depositing them over a particular region of a depression. So, over a period of time, what is happening? The height, wherever there was a height, that height is being reduced. Wherever there was a depression, that depression is being elevated. So, you have a leveling of land which is achieved. So, this is the act of leveling, and which is carried out by the process of degradation, where erosion is carried out by the agents of nature. Those eroded materials, they are transported over a distance by the agents of nature. And then you have aggradation, that is a kind of deposition. So you have degradation, transportation, and aggradation. All of them overall, they carry out the leveling of the land. Leveling of land. Okay, so that is the aspect of gradation in general. So here, this gradation can be carried out by running water. And when we say running water here, running water refers to the river movement, river or stream movement. Then, many of the times, this is what is also referred to as fluvial landforms. Then we have underground water. Now, water which is present in the region of the underground level or under the rocks, or even on the surface when they penetrate into the rocks, they carry out erosional or depositional features by eroding the portions and the faces of the rock. Whichever portion is, let's say, chemically soluble in water, those portions will be eroded, and you have large underground landforms, caves, pillars, etc., which are created. So that is by the chemical action of water. Chemical action of water. Then we have glaciers, the most massive chunks of ice which move down the slope of the mountain. That is what we regard as glaciers or the glacial movement. Now, these glaciers basically, you will observe that they come down the slope. In general, in most of the cases, they will come down the slope from the mountainous areas. In many of the regions, for example, closer to the poles, the glaciers also end up moving across slightly flattish surfaces. In many of the cases, when we talk about the history of the planet has gone through the various different phases of, let's say, ice age and deglacial period. So during that phase, the planet has observed the movement of glaciers in the present day region of Europe and America. So there also, the movement of glaciers across the surface has created a lot of glacial landforms, and so has wind and sea waves. So all of this we are going to analyze as we move ahead. First of all, we shall take a look at the stages of river movement. Before that, we take a break and then we continue. Okay. Mohammed, yes, similar as placer deposits. Palak, floods caused by erosion. So that is something, Palak, you will get a better idea when we come to Indian geography, when we talk about the property of Himalayan rivers, peninsular rivers, and also the shifting of the river channel, stream bank erosion. You will get a better idea about how is it that erosion can lead to flooding. Basically, the very brief gist is when the rivers erode something, they will deposit it in the channel. That means they have lesser volume to flow in that river channel, and in rainy season that will overflow. Yes, Kishan, that is correct. Uh, Anywhere, if I see agent of something, agents of gradation means the factors which create that gradation. Agents of nature, the forces of nature, that is what is indicated. How underground water will come to underground water region and underground landforms, wait for it. Okay, so we take a break and then we come back and we continue. Yes, Vivek, gradation is a kind of leveling. A confirmation about the audio, please. If the audio is clear and available, thank you. We'll come to the underground region also, that how that landform is created, we'll come to it. Have patience. So when we talk about, let's say, the river movement, first of all, let us understand the stages of river movement. So basically, in almost every case, you will come across a situation where as the river moves, it follows the simple law, the law of gravity. You will never come across a situation where the river has originated at a lower height and is moving to a greater height. It will never happen. Water will never end up moving up the slope. Water will always come down the slope, right? So, always it originates, the rivers originate at a greater height and come down the slope. Now, for example, take the case of the Himalayan rivers. They originate at very high altitudes, 5,000, 6,000, 7,000 meters above sea level. And they drain down, they come down. As they are moving down, they have an incredible speed, very high speed. And when the rivers have, let's say, very high speed, any agent of nature for that matter, let's say if it has got very high speed, it will be able to carry many materials with it, right? All of us would have seen that when the river is moving with a very high velocity or a very high speed, it ends up carrying all the various different kinds of material with it, be it tree trunks, be it rocky pieces, rock portions, everything is carried. So accordingly, the movement of the river can be divided into three different stages. The first stage, which is also the upper course of the river, that can be regarded as what is referred to as the youthful stage. Youthful stage of the river movement. Now try to associate it with the kind of youthful stage associated with also the humans. When you are in a youthful stage, what is something which is experienced? A lot of energy, a lot of impatience as well, and wherever possible, it will try to move, right? So that is something which is you associate with youth, a lot of energy. So in this stage, the river has got a very high amount of energy. It is coming down the slope. So here, if you think about it, very high speed. Very high speed. Now, if the river, let's say, is coming down a slope with a very high speed, it will slowly and steadily degrade the slope, deepen the slope. It will carry out vertical deepening. And in the mountains, you will never come across any river which is very wide. In the mountains, the rivers are actually narrower, but they are very deep because they have significant amount of water which digs into the ground because of the force that the river has. So that is why you'll find here deepening of the river by vertical erosion. Vertical erosion, that is going to be very high. Then also carrying capacity. Carrying capacity refers to what is the amount of material that any agent of nature can carry. So as long as the river or any agent of nature, let's say wind, anything, as long as it is moving with a very high speed, it will be able to carry a lot of materials along with it. When the speed reduces, its ability to carry materials that reduces. And that is when it starts to deposit materials. It starts to deposit substances on the sides. So that is where you will observe that, let's say, a river is hurtling down the slope with a very high speed. It will be able to carry a lot of material. So we can have a conclusion that carrying capacity of any agent of nature is directly proportional to the speed. If the speed is high, more materials will be eroded, more materials will be carried. As soon as the speed reduces, whatever materials it was carrying will start getting deposited. So here you'll find formation of deeper valleys. Formation of deep valleys. Okay. Minimal amount of deposition. Amount of deposition. The rivers are narrow but deep. Rivers are narrow but deep. Take the case of any river, any Himalayan river. Indus, Satluj, Ganga, Brahmaputra, all of them. As long as they are moving through the mountains, they will be very, very narrow, right? But they will be very deep. When I say very narrow, doesn't mean it will be like a small nala or something or a small drain. No, it will still be very significantly wider than that. But as compared to what you observe in the case of a plains, it will be much narrower in comparison. Then, after that, let's suppose there is a flatter portion of land that the river encounters. And there, as the river encounters, let's say, a flatter piece of land, a plain region, immediately what happens is that its speed reduces. And that is what is the middle course, or what can be referred to as the mature stage of the river. Mature stage. Now, as in this case, the speed has reduced because now you encounter the plain area. As soon as the speed has reduced, it will start depositing materials to some extent. But now, rather than carrying out vertical erosion or vertical deepening, the river starts flowing, it will start broadening, it will start widening by carrying out materials from the sides. It will start eroding the materials from the sides of the river. So it will not go much deeper, it will become much broader. So here you have broadening or widening of the rivers. Deposition is initiated. Initiated. Why? Because the speed is reduced. Okay. So all the materials that it was carrying earlier, that will start getting deposited now. Right? That is where whenever you take the case of, let's say, take the case of river Brahmaputra, take the case of river Ganga. River Ganga, for example, it enters the plain area where? Around the region of Haridwar. Now there, as it enters, immediately the river starts getting broader. It will start depositing substances that it has carried from the region of the mountains from the youthful stage. It will start dropping them. It will start depositing them. So depositional features are created in the process. And as is the case with the mature stage of life in general, the energy is a bit controlled. You have a fixed channel of flow where the river will continue to flow. It will not go here and there and randomly move to a different place altogether. So there is a kind of a fixed nature of flow. So here, then you have the lower course, or what is also referred to as the old stage. Now, in the old stage, the level of the land is almost similar to the level of water which is present. In the sense, level of land is almost equal to the oceanic water or the sea where the river is eventually going to drain. So, in that situation, the speed is absolutely minimal. Speed is minimal. Okay, the speed is very, very slow. Then, if the speed is very, very slow, means deposition is maximum. and almost no erosion. No erosion. Okay, so this is basically where you will find a lot of depositional landforms which are created in the process. So this is the classification in terms of the stages of river movement that you can come across, that you can think about. Okay, so that is the youthful stage where the speed is very high. So where, if you will observe, the rivers are narrow but they are significantly deeper, right? That is the vertical erosion which is happening. In the mature stage, the river will be very wide, not as deep, but comparatively less deeper as compared to the youthful stage, but it will be very, very wide. And then in the old stage, it will deposit a lot of materials. And in this process of erosion and deposition, it ends up creating landform. The speed of the river is always determined by the slope. If the slope is predominant, speed will be high. If the slope is less, the speed will not be present at all. So, now with that basic concept, let us take a look at the erosional and depositional features. Now, before going into that, I want you to keep one other thing in mind. We have seen earlier that due to the forces acting from the interior, the land sometimes can get uplifted, the land sometimes can get subsided. That can always happen. The land, when it gets uplifted, varies ever so slowly. When the land gets uplifted, the rate of uplift is maybe around, let's say, 50 or 1 centimeter every decade, or 1 centimeter every 5 years. That is the slow rate of upliftment which can happen. So let's assume there is a river which is draining in a region. Let's suppose in an area, the river is draining like this. Now, due to internal forces, let's suppose this entire region, the dotted line, this region experiences a kind of an upward lift, an uplift. Ever so slowly, let's suppose it tries to lift itself up or rises up. Now, the rate of uplift will be very, very slow. Now, here, what do you think will happen? Will the river movement come to a stop? Or will you come across a scenario where the land's upliftment is so slow that river will continue to flow in its own path, will continue to erode whatever is happening in its path all around it? The land keeps on getting rising up. So that is something that we will observe in the case of the landforms, where we will find that as the land gets uplifted, the river will continue to erode and will continue to follow its original path as the land around it changes its shape. So let us take a look at it, and let us try to understand how these land features are created. So you have a host of erosional landforms. Most of them, most of the erosional landforms, you'll find to be present in the youthful stage. A couple of them you'll find to be present in mature stage. Now, both these that you find in the mature stage, they are created due to uplift of the land. Due to uplift of land. Yes, perfect, Sachin. That is what is rejuvenation. Now then, the depositional features. The depositional features, when you come across, so most of them, almost all of them, you'll find in the mature or old stage. Old stage. Only this is the depositional landform that you still find in the youthful stage. Okay. And I had a question from Ved Shri. I read Ganga is shifting. So is it due to erosion? So that shift in the Himalayan rivers happens due to the substances which are present. Some of the Himalayan rivers, they change their course due to excess deposition that they are able to carry out in their own course, obstructing their movement. In Ganga, it is not such a significant shift. In rivers such as Kosi, the shift is very significant. Again, to be covered in the portion of Indian geography in the river systems. We'll cover each of them in detail. Don't worry. So, here, let us take a look at each one of them. Let us try to understand how they are created. So, first of all, we shall take a look at valleys and gorges. It is not Georges, okay? It is not Jorges, it is gorges, okay? So, what are these? So, the basic profile, if you take a look at it, if you take a look at the basic profile of it, so valleys will indicate a kind of a V shaped structure where the slopes, they are not very steep. So the valleys will end up indicating a kind of a V-shaped structure, broader, little broader at the base. Observe the river moving here. The river is moving somewhere across this particular region. If you are able to observe the image, that is where the river is. But the river might very well come somewhere here, might very well come somewhere here. So that is the case of a valley. When we talk about a gorge, gorge is basically almost similar, but the walls are vertical with a very narrow base. That is what is referred to as a gorge. So when we talk about it, valleys are depressed areas of land scoured, means eroded and washed out by the forces of gravity, water, and in many cases, even ice. The resultant structure might end up having a kind of a U-shaped profile or might end up having a broader V-shaped profile. That is formed in the case of a valley. And when we talk about gorges, they are very deep, narrow valley with very steep sides. This is what you have as gorges. Now, both of them, they are created in the youthful stage of the river. As the river moves down the slope with a significant speed, it is able to carry out vertical erosion. Vertically, it is able to dig it out. So that is where it is able to create these deeper structures, right? So both of them are a resultant of vertical erosion by river. Okay, both of them, they are resultant of vertical erosion by a river. Sometimes what happens is that a gorge over a period of time that can get converted into a broader valley shape. How? So let's suppose you have the presence of this gorge here. You have the presence of this gorge. Now, over a period of time, this has been created due to vertical erosion of the river. That is where it has gotten so deep. Now, over a period of time, the sides of this, they will get weathered due to the exposure to, let's say, rainfall, wind, solar insolation, etc. There will be weathering which will happen. Materials are reduced to smaller particles. Now, these materials will slide down the slope when you have availability of rainfall. Anything which happens, it will slide down the slope. And eventually, what do you have? You have a broadening and you have a formation of a valley. So in many of the cases, the gorges, they broaden over a period of time due to weathering and mass movement, and that leads to formation of a valley like shape or a valley like structure. Okay, now we come to the concept of potholes and plunge pools. What are these? Potholes, something for which you don't need to go to a particular mountainous area. Nowadays, potholes are very prominent even in the region of the roads that we travel through. We get a very normal sighting of these particular areas in our roads also. So, what are these potholes? How are they created? They are created by the action of the river. Now, potholes means small depression. So, how do they get created? Let us understand that. So, here, when we talk about it, let's suppose difference between U-shape and V-shape valley, Namita, is very simple. The base of it will be broader and uniform, that is a U-shape. If the base is slightly narrow, it will be a V-shape. So let's suppose here we talk about a river in its youthful stage. That is, it is still draining down the slope. Okay? It is draining down the slope. Now, when this river is draining down the slope, the speed will be high, isn't it? The speed will be high. Now, when the speed is high, what will be the carrying capacity? The ability to carry substances will also be very high, right? So, carrying capacity will also be very, very high. Okay, so it will be able to carry a lot of materials along with it. It will be able to carry large rocks and boulders along with it. So here, let's assume this is carrying some large rock, right? Now, when you would have observed this, especially if you go to the region around Rishikesh, or if you go into the region of, let's say, around Ladakh, or if you happen to venture into the region of Arunachal Pradesh, there you observe these phenomena very frequently. Whereas the river is coming down the slope, it does carry many of the rocky particles which keep on rolling along the riverbeds. The larger rock particles, it is not as if the river will be able to throw it like a thermocol. It will be carried, but it will be carried in a very different pace. So here, let's suppose you have a large rock which is being carried. Now, this large rock will be dragged across the surface because it is heavier. So, owing to the weight of it, it will hit the ground. Now, when it hits the ground, there is a force which is created. The ground will have an ever so slight amount of depression which is created. Something which is not even noticeable, but a small amount of depression which is created. The rock will bounce back, will then again drop somewhere here, creating a small depression. The rock will then bounce back, will again form a depression here, and so on. It rolls away. Now, the next rock which is being brought by the river, the next rock which is brought by the river, that next rock, let's suppose, also ends up dropping somewhere in the same region. So, what will happen? With every such strike, it will get deeper. All of these will get deeper. Now, beyond a point, on the riverbed, if let's say you have certain deep indentions, certain depressions on the riverbed. Now, what happens as a result of it? This will induce some kind of a water movement. Water will naturally try to come down and naturally try to come out of that small hole. That means all the big rocks which are coming with the water, they will naturally be attracted to that hole. They will hit it with all their might, and then they will move ahead. A repetition of this process, a continuous repetition of this process on the riverbed ends up creating these small depressed areas. Eventually, due to the movement of the water, many of the smaller rocks also will get trapped, will move as the water tends to move slowly and steadily. The holes will be widened, and that is what we refer to as potholes. So potholes are also to be found in the youthful stage of the river movement. So formed because of stream erosion aided by the abrasion or the hitting of the rock fragments. Once a small and shallow depression forms, pebbles and boulders they get collected in those depressions and get rotated by the flowing water. Consequently, the depressions they grow in dimensions, they become larger in size. So again, think about it. If you have a river movement happening down the slope, river will carry a lot of materials, including large rocks and boulders. Those rocks and boulders, they will hit the base and they will be dragged on like this. So as they hit the base, a small depression will be created here. That will automatically induce the flow of water, where the water will be dragged in and then will be thrown out. That means more rocks will be dragged in, hit that depression, and move ahead. A periodic and continuous such hitting will lead to the deepening of that particular region. The river bed will start deepening. And that is where, when the river bed starts deepening, you will have a lot of these small components, pebbles, etc., which will get trapped there, which will deepen it up. And that is how potholes are formed. Uh, Krutika, all the potholes are only made by the rocks? Yes, in the case of the rivers. And Lakshmi, how are you linking the concept of youthful, mature, and old stage with the subsidence and upliftment bent? We'll come to it, don't worry. And potholes that you find on the Indian roads, that is because of poor construction. That is it. Every valley can trace back to a gorge in many of the cases, in most of the cases, but not in all of the cases. Is it possible that exogenic force is stronger, that it overrides the slow endogenic force? Yes, absolutely possible. Okay. Now, right now we come to the plunge pools. What are plunge pools? So plunge pools, for examples, Pooja, these are the examples. If I tell you 5 kilometers from Rishikesh, you find a pothole, will you be able to associate with that example? You will never be able to associate with that example if I give you the name of those potholes. So think about it. That is why I have given as many images as possible so that you can associate with it. By example of pothole, we possibly cannot end up indicating to you that, in the river valley or in the river of Ganga, for 400 kilometers from its origin, you have a pothole which is created before Rishikesh, and that pothole is extensive for around 4 to 5 kilometers. No clue will come across your mind that what am I talking about. So here, the best examples are the visual depictions that you can get. Okay. Potholes upper in narrow and lower in wider. What? Upper in narrow and lower in wider. Please frame your question carefully, guys. Do valleys form into gorge, or is it vice versa? Gorges form into valley. Valleys generally don't end up forming gorges. Now we come to the portion of plunge pools. Plunge pools. Potholes are very small, guys. Potholes are not so large. Potholes, think about it, the diameter of your leg, sometimes even slightly more than that. That's it. That is the pothole. Not much greater than that. Now we come across the plunge pools. Now, how is it that plunge pools are created? So, when we talk about plunge pools, generally to be found at the bottom of a waterfall. Generally to be found at the bottom of the waterfall. So, when you have a river water which is moving, let's suppose this river water, in the case of the waterfalls, they will end up falling here, right? They will end up falling here, and then they will end up draining in this direction. That is how the river movement happens. Water keeps on coming in, Water keeps on falling. Water keeps on falling. Now, as the water keeps on falling, it will exert a pressure on the ground. It will exert a force on the ground. Slowly and steadily, it will lead to deepening of the ground in this region. Because of the force of that water, water will bring some substances also. So slowly and steadily, water will get deepened in that region because the land will get eroded by the force of that water, continuous hitting of that water. So this particular depressed area, this is what is referred to as plunge pool. That is why it is always advised never to go directly underneath the waterfall. Right? Every year, hundreds of people they lose their lives in these plunge pools. Because what happens is when you generally go to a tourist place where there is a waterfall, as you are walking down in this particular region, the water will come, let's say, beneath your or at a portion at your knee level. So you are very confident and driven by the urge of the social media networks which are present around. You want to get a picture clicked directly underneath the waterfall in order to indicate your bravado, your machismo, etc. Now, when you go directly underneath the waterfall, suddenly water gets very deep. It is like a situation where, let's say, you are 2 steps before where the waterfall is, 2 to 3 steps before that, the water might come to your waist level. But as soon as you enter at the base of the waterfall, immediately it might go above your head high because there is a plunge pool. And in the region of plunge pool, suddenly when you lose your footing, you end up going down in water. And it is very difficult to come up in that region again because the water is pushing everything down with a great force. That is where the amateur swimmers, in that sense, even those who know swimming but don't know it significantly well, and if you are unable to find any footing around you, there is a high probability that there is a dangerous outcome which is going to happen. So that is why always advisable never to go directly at the base of the waterfall, regardless of how good an image it will give you on social media. Never go directly under the base unless and until you know what is the depth of it, because you might have a deep plunge pool lurking underneath. Okay, that is the creation of a plunge pool. So, valleys, gorges, potholes, plunge pool. All this basically is formed in the youthful stage of the river itself. Then we come to the mature stage. Mature stage is generally where you don't experience any form of speed in the river. You don't expect any erosional structure, because in mature stage, as the speed of the river reduces, rather than flowing through a straight line, river starts following a kind of a wavy nature. Okay, so there is a wavy nature which is referred to as a meander. That is something that you observe in the mature stage. So in the mature stage, you also have creation of landforms, sometimes erosional landforms, initiated by the uplift or the subsidence of the land. The land can get uplifted or subsided. How? Let us understand that. So here, take a look at the first image A here. Now, if you observe image A, this is a level at which the water is flowing. It is a mature stage. The speed is slow. So the water follows a kind of a meandering path. Now, let's suppose in the same region, let's suppose there is an uplift of land. Why will there be an uplift of land? Due to endogenic force. That is, force acting from the interior of the surface. Heat can be provided, land slowly and steadily can get lifted up. Right? Very slowly and steadily, it can get lifted up. Now, that rate of uplift is going to be very slow, right? Rate of uplift is very slow. Beautiful, Sachin. Very nice. Impressive. So that rate of uplift is very, very slow. So that means you can have certain amount of consequence as a result of it. What is the consequence? So think about it. Let's suppose there is a landmass. Let's consider the cross section of the river flow. Let's suppose this is the landmass across which the river is moving. And think about it carefully. Observe it logically step by step. You will understand it once and for all. And it is in this river channel where the river is moving. Now, when I say the land is getting uplifted, so here, this will get uplifted. Here it will get uplifted. Here it will get uplifted. This will get uplifted. Even this will get uplifted. Isn't it? Maybe by, let's assume 1 centimeter every 5 years. Every 5 years, the land is uplifting by 1 centimeter. Now take a look at it from a cross-sectional or a top view. From a top view. The same river. Let's assume that the same river is moving in a region here. Now in this area, if this particular section spanning across, let's say 500 kilometers, if this section is experiencing an uplift, that is what we have depicted in the first figure in a cross-sectional manner. Let's suppose this is a region which is experiencing a kind of an uplift. Now, when it is experiencing a kind of an uplift, observe, here land will rise, here land will rise, here land will rise, here also land will rise. The land will also rise at the bottom of the river bed. But think about it. The river is flowing along its path. Suddenly, the river experiences that on its river bed, there is a protrusion or an elevation by 1 centimeter. The river is flowing naturally. Suddenly, when it enters a region, it experiences that the river bed has been uplifted by 1 centimeter. What will happen? The river will start acting upon that 1 centimeter elevation. Slowly and steadily, it will carry out the erosion of it. Isn't it? That elevated portion, it will get eroded. So, at the river bed, because the river is flowing in continuity from a distance before it and even after it, the river will maintain the height of the river bed. Because the rate of erosion is so less, any elevation which has happened on the river bed, the river will be able to erode it. But what about the sides of it? The sides, this region, what about that? The river will not be able to erode it. It will continue to get elevated. Again, after 10 years, let's say there is another 1 centimeter of elevation or increase in height. Again, the river, as it is moving, it will maintain its own path. In its own path, if there is an elevation of 1 centimeter, immediately it will be eroded. But all around it, it will continue to get elevated over a long period of time. As this process continues for hundreds of years altogether, what do you observe? You will observe that the river has maintained its own path. The river bed's height is the same because whenever elevation has happened, it has basically been eroded, whereas all along the sides of it, the land has uplifted. So this is basically referred to as what is an incised meander. Incised means something which has been carved in. It appears as if it has been carved into this. For example, take a look at this. This is an incised meander. Now observe here, you will observe that where the river is moving, it is moving in a kind of a meandering fashion. But all around it, the land is significantly uplifted. Now, just by taking a look at the image also, you can gain an idea that when is it and how is it that the land would have been uplifted. For example, observe here, the walls are vertical, means this entire region would have been uplifted almost continuously without any stoppage, in the sense that 1 centimeter every 2 years, this would have been a continuous process. Observe this particular portion. You will observe some bands around, a kind of a layering around. Each of them would indicate a different phase of uplift, that it would have been rising up, let's say, for 500 years, for 1,000 years, and then there would have been a pause. Then again for 500,000 years, and then there is a pause. So this is what is an incised meander. This is observed in the case of North America by Colorado River. In India, it is observed in the Ranchi Plateau of Chota Nagpur region. So this is observed generally in very old areas of the planet where the land has undergone multiple differences between uplift and downlift. Okay, that is basically an incised meander. Now, a similar process is observed when we have the formation of what is referred to as river terrace. River terraces. River terraces here also result of an uplift in the mature stage of uplift of land in mature stage. Now, think about it. Suppose here, let's suppose this is the region where we experience a river movement. Okay? Let's suppose this is the landmass. Now, here, let us assume that the river is moving through here. Now, over a period of 500, 600 years, it is not always going to be present in the same region. It might also happen that the river might end up flowing through this particular area. It might end up flowing through this particular region also. So the river will have its own entire plain sort created. Now here also, let us assume that there is a similar process which is going on. That is, there is a phase of uplift going on. Uplift is going on. The land is getting uplifted. Now, again, all of us who are unable to fathom a situation that how can a land get uplifted on its own without any superhero doing it, how can the land get uplifted? It is created when you have enough heat in the interior that sometimes pushes up the land above, as we have studied in the case of convection current also. When you have the heat present, sometimes the land can get pushed up. So that is where once the land gets pushed up, it is referred to as an upliftment. So if the upliftment happens in this case, there will be upliftment all around the sides, but where the river is moving, there the river will continue to maintain its own path by eroding any upliftment on the river bed. So after some time, you will come across a scenario where if this portion has uplifted, let's suppose this portion, let's assume, has been uplifted, the river has maintained sort of what has been its original path. So here, the river will flow across this particular path. But the river, again, over a period of 100 years, 1,000 years, and so on, it will continue to move around. It will broaden this particular valley of sorts. So after, let's say, 100 years, 200 years, this particular region would have become much, much broader. And let's assume this becomes significantly broader in the sense that it becomes somewhat broader from both ends because of the movement of the river, wavering of the river from side to side. It has become significantly broader, let's assume. Okay, this has become much more broader because the river has carried out its erosion. Now, again, if there is renewed phase of uplift, again there is uplift, let's suppose. So wherever the river is draining, it will erode everything on the river bed, but all around it, the land will be uplifted. So what is the shape it will indicate? It will indicate a very unique shape here. The portion which was already uplifted will rise up even further. Then this particular portion at the base, this will also get uplifted now. Then you will have a portion of river movement, and you will have a profile somewhat like this. Okay, you will end up observing a kind of a profile somewhat like this, where now this is where the river has been draining, and all around it, it has gotten uplifted. And now it indicates that there have been two series of uplifts. Now this will again get broader at the base. And let's say if there is an upliftment again, what you have is the case of a step-like feature on the sides of the river, a result of multiple different such stages of uplift. That is what is referred to as a river terrace. So when we talk about a river terrace is created due to the uplift of the land. So again, I will repeat the entire process. Listen to this very carefully. So when we talk about a river moving in the mature stage, let's say a river is moving in the mature stage. Now, no, it is not always symmetrical. Let's suppose the river is moving in a mature stage here, and there is an upliftment of the land. Now, as the land gets uplifted, wherever the river is flowing, there it will continue to flow, it will continue to erode the riverbed as the land all around starts to get elevated. As the land starts to get elevated all around, here you come across a structure somewhat like this. It is much more narrower in the initial stages. The depression is much more narrower, but over a period of time, what will happen is that the river will continue to broaden. As was the case in the first scenario, the river will continue to broaden. So it will continue to broaden the valley that it has created. Now, after that, if another uplift will be created or will occur, this portion which was already elevated, this will be raised further higher up. And this portion which is at the level of the valley, this will also get elevated. The river will continue to have its own place at its own level. So there will be an elevation somewhat like this. So you have a step-like feature due to multiple different levels, all of them getting elevated. So you will have multiple step-like feature. That is what is referred to as the river terrace. Okay. Ashutosh, diagram is compulsory for mains exam. Absolutely. My drawing skill is not so good. My drawing skill is also not good. Even this basic level of rudimentary diagram, if you can draw it, that is more than sufficient. UPSC is not searching for the next MF Hussain to be an IS officer. UPSC is searching for someone who can depict what they try to, or what they are trying to convey, that is depicted by diagram. So a simple diagram, even at this rudimentary level of diagram, if you draw, more than sufficient. Okay. uh Vishnu Maya, yes. This could happen in meanders as well. Smriti, yes, it can also happen in meander. And Shalu, pothole is depressed area where waterfall. No, that is basically when we say at the base of the waterfall. This, when we talked about, this is a plunge pool. Pothole is when in the upper course of the river, in the youthful stage, it hits the base. That is what is a pothole. Okay, right? Incised meanders looks like gorges. Sometimes gorges also get created in a similar process. We'll come to it when we come to the river systems and we talk about antecedent river systems. When we'll take the example, let's say, of Indus, Satluj, Brahmaputra, Kosi, they have created gorges in a very similar manner. We'll come to it in Indian geography. Why do water in meander move in a zigzag manner? Due to depositions, basically due to very slow speed. And depositions also happen, but because of very slow speed. Does meander and river terrace depend on the nature of flow? Yes. See, all of you who are thinking about it, that whether the water will flow in a straight manner or in a kind of a zigzag manner, do this experiment at your house. Take one small cap of any bottle, fill it with water, put it on the floor, assuming that the floor is, let's say, a floor is absolutely flat, no slope in any direction. You'll find that that water finds it very difficult to move in a different region or in any direction. Even if it is moving, it will never be moving in the straight manner. It will try to find a wavy pattern, it will try to find a slope. But if you pour a jug of water, it will always move in a straight line. Why? Because that jug of water, when you pour on the ground, it provides the speed. So whenever there is a speed, water will always move in a straight fashion. Whenever the speed is not there, there's a kind of a zigzag flow associated. That zigzag flow is what is referred to as a meander. Okay? Then we come to the depositional features. Now, in the case of, yes, one river can end up making endless number of meanders. Okay? Now here, when we talk about, let's say, the depositional features, other than the alluvial fans, almost all the depositional features are created in late mature or the old stage of the river movement. Okay, so we'll take a look at each one of them. Before that, let us understand two of them, that is floodplains and natural levees. They are formed in mature and old stage. What are these? So I will be able to explain it to you with the help of the diagram, the rudimentary diagram that we will be drawing. That is where we will be talking about. When this geomorphology portion will be finished after monsoon. So here, when we talk about this, here let us assume that we have this as the region where the river is moving. Okay. Now, here, this is the river channel. And the river has been flowing for hundreds of kilometers before it. and the river has been bringing various different sediments along with it. Okay. Now, let's suppose the river floods. Now, when the river will flood, this entire portion will flood. When the river will flood, this entire region will end up getting flooded. So, as this entire region gets flooded, so all the sediments that the river has been carrying, they will start getting deposited here. All the sediments, let's indicate sediments by the whitish color. So all the sediments will end up getting deposited here. Right? And after the flood water, let's say, retreats. Let's say the flood water retreats after the rainy season. Now, when the flood water retreats, these sediments are left behind. And when these sediments are left behind, here, this is what is referred to as the floodplain of the river. Floodplains of the river. So floodplains are generally created on the sides in a plain region due to depositions carried out by the river, depositions of sediments that the river has been bringing from a large distance, depositing it on its sides. That is what creates a kind of a floodplain in nature. Then, when we talk about natural levees, so for example of floodplains, take a look at Assam plains created by Brahmaputra. Take a look at the plains in UP, Bihar, created by river Ganga. Same is the case with West Bengal and Bangladesh. You have the floodplains created by river Ganga. So here, when we talk about, let's say, the floodplains, these are very fertile areas because these have sedimentary deposits and these contribute to significant agricultural output as well. Lot of agricultural growth is observed in this region. Then let's say we talk about another situation where as the river is moving, again in a mature stage, the river will be able to carry significant amount of deposits along with it, significant amount of sediments along with it. Now, understand and apply your logic for a moment here. When a river moves like this, if let's suppose this is the movement of a river, right? I'm sure all of us would have experienced a river movement sometime or the other in our life. Now, if I ask you that the speed of the river is slower in which region, on the sides or in the middle of the river, where is it that the speed is slowest? Perfect. On the sides. So it is on the side where the speed is slowest. Now, we had seen earlier that carrying capacity is proportional to the speed. We had looked at it, that carrying capacity is proportional to speed. So if the speed is low, means deposition will start to happen. The speed is slow at the sides. Immediately at the sides, the speed is the slowest. So this is where the deposition of the sediments, they start building up ever so slowly. The depositions of the sediments, they start to happen. That is why, if you have ever actually been to a river, if you have actually witnessed a river flow, it is not going to be that it is an absolutely plain area and then you encounter a river. No. Generally, you will observe that before encountering the river, there is a slight uplift in the landmass. That is carried out by deposition of the sediments on the sides. This deposition immediately on the sides by the river, that is what is referred to as natural levee. Yes, perfect. They act as an embankment. This is what is referred to as a natural levee. Okay, so these are your depositional features. This is how deposition is generally carried out. Let us take a look at few of the other depositional features, starting with the alluvial fans. Now they are named as fans because of the shape that they end up getting. Now these alluvial fans, these are one of the only depositional features that you find in the youthful stage of the river movement. One of the only depositional features that you find. Now here, observe this. The river is draining down the mountain. Observe how narrow this river is. As it comes hurtling down the mountain, it is very, very narrow. It starts getting broader as slowly the slope, the gradient is lesser. Now, imagine the situation if you have the mountains here. Okay, let's assume here you have the presence of mountains. Now, a river is draining down the slope. River is draining down the slope. As the river is draining down the slope, the speed will be very high. So it will be carrying a lot of large rocks and boulders along with it, right? Because the carrying capacity will be very high. But as soon as it encounters the plain region, as soon as it encounters the plain region, the speed will suddenly drop. The speed will suddenly drop means the carrying capacity will significantly plummet. So all the large rocks and large boulders that it was carrying, it will get deposited immediately here in the vicinity in a kind of a semicircular shape. Now that is what we refer to as an alluvial fan. That is what is referred to as an alluvial fan. When River Kosi comes down the slope of Himalayas, it carves down an alluvial fan having a radius of 8 kilometers. And these are made up of large rocks, large deposits, immediately at the base of the foothills. That is basically what is alluvial fan. Observe here. This here indicates the alluvial fan deposits that you have. Okay. Now it resembles the shape of a fan. That is why the name alluvial fan. Okay. So this is observed in the youthful stage. Immediately when the river comes down the slope of the mountain, that is where it is observed. Then we have the meander. Meander basically means when the river follows a kind of a wavy path, a wavy pattern. That is what is a meander. So when we talk about the river forming a meander, you have to understand that it forms a meander only because the speed is not high enough. If the speed would have been sufficient, river would have flown in a straight path. But because the speed is not high enough, what happens? Let's suppose the speed is not high enough in this case. So slowly and steadily, the depositions will start to happen along the sides. Let's suppose the depositions have happened here in this region. Let's assume. And try to associate it with the flow of liquid also, flow of a fluid. So if there is a deposition which has been created here, now this river, the river water will get deviated due to this depression or this deposition rather, isn't it? That is something which will be observed because of this deposition, river water will get deviated slightly. Now that river water will end up hitting this particular portion here. And because the river water will hit up this portion, what will happen? This portion develops a kind of a wider angle like this. So now the river water comes here, is redirected by the shape. As it is redirected by the shape, there will be an indentation here also. So after some time, the river movement that you will be able to observe is somewhat like this. So this wavy nature, that is what is referred to as a meander. Over a period of time, observe this, the river is moving in a kind of a wavy nature like this. That is what is referred to as a meander. Okay, over a period of time, this meander gets accentuated in the sense that the waves, they become much more prominent, because as the water will flow, it will attack this particular portion, then it will attack this particular portion, then the water flow will attack this particular area. So over a period of time, this meander gets much more wavy in nature. The wavy nature keeps on getting exaggerated. And that is where sometimes you have a wavy nature which is so much exaggerated. Let's suppose a meander gains a shape somewhat like this. Now, after some time, it might happen that water, due to erosion in this region and erosion in this region, water of these two meanders, they might end up meeting. So if the water ends up meeting in this area, then the river water will come like this, will drain through this shortcut path, and will no longer be required to drain through this elongated portion, because now it has become joined. So over a period of time, the connectivity of the longer portion gets dismantled, because now water has found a significantly shorter path to flow. Water has found a kind of a shorter path to flow. And that is where the earlier meandered portion, that gets isolated. You have accumulated water in a kind of a horseshoe shaped format. And that is what forms a large lake, which we refer to as Oxbow Lake. Oxbow Lake. That is what forms that large lake. For example, observe this here. So in this case, observe here. This particular portion of the meander has now gotten separated because the water has found a shorter path. So this is what is an oxbow lake. Now this oxbow lake, when it comes to the rainy season, it might absolutely happen that this oxbow lake might again get reconnected for a brief moment due to excess of water flow. But again, during the dry conditions, this will be isolated. So that is what you have as an isolated region, that is Oxbow Lake. Okay. Now, then after that, we come across another feature that you observe in the mature stage of the river, generally in the older stage of the river to be more precise, that is the braided channel observed in older stage. Oxbow Lake is found in India in many different areas. If ever you get an opportunity to travel through the northern plains of the country, east to west to east, a lot of these Oxbow Lakes created by River Ganga, its tributaries, all of them end up creating these oxbow lakes. Few of these oxbow lakes, they are also regarded as critical wetlands for the conservation of species. So here we come across braided channels which are found in older stage of river. Yes, oxbow lake is always to be found in the vicinity of a meander. So basically what happens whenever you have a meander, let's suppose like this. Now, if due to erosional purposes, these two end up meeting together, so now the water will find a shortcut of flow directly from here. It will never move through that large region. So as a result of that, when the water does not flow there, this region will get disconnected. And that is where the particular area is referred to as an oxbow lake. That is the entire formation of oxbow lake. Now we take a look at braided channel. So braids or braided generally associated with the kind of the hairdo, a kind of a hairdo that you come across, intertwined structure of sorts. So here when we talk about the braided channel, observe this entire river flow. Here it appears to be an absolute intertwining of sorts. So in the old stage of the river, when the speed is very low, when the speed of movement or the speed of motion is very, very low, in that situation, deposition is very high. Deposition is very, very high. And when the deposition is very high, materials are deposited in the river channel itself. Materials get deposited within the river channel. So observe here, the deposits have been dumped into the river channel itself. All these are deposits. So if there is a river flow, imagine that all these deposits are dumped across the river channel itself. So as a result of that, there is no such unified flow associated with the river. Rather, it will appear to make many such small streams which are intertwined with each other. And that is what is regarded as the braided channel. So it is across these areas where it is very difficult to distinguish which is the main flow of the river and which are these side channels which are included. It is very, very difficult to have a distinguishing note. So all these are basically deposits, right? And the river flow is restricted into these areas. So all the major rivers in their older stage, be it Brahmaputra, be it Ganga, be it Indus, all of these, even the peninsular rivers in many of the cases, for example, Godavari, that also ends up creating a kind of a braided channel in existence. So that is how the braided channels, they get created. Okay? Formed when the speed is very, very slow. Okay, so that is what we have as the braided channel. Then we come across the final depositional feature created by the river, that is a delta. Now, a delta is created before the river meets the sea or at the point when the river meets the sea. So, if the river is able to carry significant amount of sedimentary load, now as soon as it is meeting the sea is at the same level. So the speed of the river is absolutely reduced. It is opposed by the sea. So the speed of the river drops down to somewhere around zero. So that is when all the finer particles that the river was carrying, because the larger particles have been dropped much earlier, the finest of the fine particles that the river has been carrying, because the speed has now suddenly reduced, all those particles will eventually get deposited in this region. That is what is referred to as a delta. This is basically what is referred to as a delta. Deposits of finest particles. Now these are very, very fertile because these deposits, they are enriched almost every year with newer materials brought down by the rivers. These are enriched every year. Example, Sundarbans Delta. The largest delta in the world is the Sundarbans Delta. Then the deltas created by Godavari, Krishna, Kaveri, Mahanadi, all of these are also very fertile. So this is basically the final depositional feature created when the river meets the sea. Observe, this is the sea. This is where the river is flowing. Suddenly, the speed reduces to zero and all the deposits end up happening in that region. That is what is referred to as a delta. Then we come across the landforms developed by in the underground region by water. So here, many of the times, when you have the water moving into underground areas, that ends up creating large cavities and large cavitations where you have a lot of materials which are dissolved by water. So this is created purely by the chemical solubility of the materials in water. In other words, this will be observed only in those regions where the rocks consist of materials which are completely soluble in water. So, here, found in the areas, braided channels are created in the older stage, much before the delta formation. You will observe braided channel. Is alluvial fan and delta related? Absolutely not. Why will that be related? One is found at the foothills, another is found where it meets the sea, right? Anything which resembles in shape does not mean that is the same thing. Okay, if the shape is similar, does not mean it is the same thing. Potato and oranges, very similar in shape. Are they the same thing? No, right? So many of the fruits resemble in shape. Are they same? No. So just because you observe the kind of a similarity in shape doesn't mean. I have already told you that when we talk about alluvial fans, they are formed in the youthful stage. And when we talk about delta, they are formed at the last stage. So where is the doubt if they are the same or not? Let me know. Yes, Chaitanya, perfect. So this basic reason for Sundarbans to be so vast, because lot of deposited materials carried or eroded materials carried by the vast river of Ganga, Yamuna, Brahmaputra, all of them are deposited. That is why it is so vast. In delta region, sometimes you will find the braided channel, but not always. It is very minimal. Braided channel you will start finding. For example, take a look at Sundarbans where they are. Braided channels will be observed in river Ganga right from the region of east of Bihar, West Bengal, etc. Similarly, when we talk about Godavari, braided channels will start getting formed around 50-100 kilometers before the delta formation. In the case of Brahmaputra, as soon as Brahmaputra enters into Bangladesh from the Dhubri region of Assam, there itself braided channel starts getting formed. Okay. Now, found in those rocks which consist of materials soluble in water. Soluble in water. Right? For example, calcium. For example, if you talk about it, calcium found in limestone. So when you have limestone, limestone is very significantly rich in calcium. Okay. Limestone rocks consisting of calcium. So the water, wherever it finds these materials which are soluble, it will keep on dissolving them. And eventually it might find an exit path altogether. So it forms erosional landforms in this manner and also certain depositional landforms. This is what is also referred to as karst topography. After the karst region in the erstwhile Yugoslavia, where it was first of all discovered. Okay, so that is where you have the name karst topography. So here, let us take a look at this particular portion. That is, you have the erosional and the depositional features which are created. Now, let's suppose you have a kind of a landform like this, which is rich in limestone and rich in calcium as a result of it. Now, in this region, let's suppose you have huge amount of rainfall. Is karst topography present in India? Yes. If you happen to venture into Meghalaya or parts of Karnataka, some parts of Madhya Pradesh also, you'll find this. Let's suppose there is high amount of rainfall. Now this rainfall will start dissolving the materials here and there, right? Wherever you have these materials available which are soluble in water, it will start dissolving them. Right? Now, over a period of time, this will create large holes, very giant holes, right? Because the materials, they have consistently dissolved it. So over a period of time, it creates very large holes. The size of it is much, much larger than what you saw in the case of a pothole. These large holes, which are created on the surface, this is what is referred to as a sinkhole. Just to give you an idea about the size of it, look at this passage on the sides. This is actually a very large road. So that gives you an idea about the size of the hole also. Observe here also the hole is getting created or has gotten created. And observe how slowly this hole is merging with the other one which has been created. So over a period of time, this can get merged, isn't it? Over a period of time, this can get merged. Over a period of time, continuous erosion can lead to a merging of this as well. Isn't it? Over a period of time, this can lead to a merging of this as well. Why? Because the materials, they are soluble in water. If they are soluble in water, slowly and steadily, water will keep on dissolving them. So it can happen that many of these holes, they get together and they form what is referred to as a valley sink, a valley of all these sinkholes. So when they get together, it forms a valley sink, or what is also referred to as uvalas. Yes, you can also refer to as polias, but it is generally referred to as uvalas. So observe this. So initially, this is how the sinkholes are created, very large in size. Okay, very, very large in size. Now, if they get together, if the entire portion is eroded together, that is when you have the formation of these large valley sinks, which we refer to as uvalas. Okay, now sometimes as the water comes in, as there is rainwater or rainfall which happens, now that rainfall, let's suppose it starts dissolving the materials. It starts dissolving the materials here. Now, as it starts dissolving the materials, it will continue to erode and dissolve the materials as long as, let's say, calcium and other such soluble substances, they are present. And eventually, they will create a large a large depression of sorts, and they will exit themselves somewhere here. So that creates large caves. That ends up creating very, very large caves. Many of these caves are interconnected. In the mountainous areas of around Meghalaya, if you will go, you will find many of these caves which move from one region to another, and they can last for many, many kilometers. Oftentimes, tourists would get trapped into that, never to come out, never to be found again, because you never know where that cave would lead to. Because wherever the materials which are soluble in water would be present, they would the water would continue to erode it, continue to dissolve it. So that is where these caves now, it is not allowed to venture into these caves. The government of India has put up a kind of a closing board or closure notices in all the areas around. Now, when we talk about these caves, these are basically created due to the process of erosion, right? So these are also erosional landforms. Okay, so the erosional landforms, sinkholes, uvalas, and caves. Uvalas, they are formed when multiple sinkholes they get together. That is what leads to the creation or the formation of uvalas in general. And then after that, the depositional feature. How is it that the depositional feature has been created or is getting created? So when we talk about, let's say, a particular region of a cave, let's assume we talk about a cave. Let's suppose we talk about a particular cave in general. Now, if ever you have noticed in older houses, again, government houses, where there is a lot of seepage, or government run educational institutions or your colleges or your school, if ever you have noticed seepage from the top of the ceiling, from the roof, I'm sure you would have observed it sometime or the other in your life. Now, there, what do you observe? It is not as if the water is seeping, it will directly start draining out like a river. No. You observe basically that small droplets, they are formed initially on the top of the ceiling. Small droplets are created. These droplets, they start getting bigger and bigger and bigger. And eventually, when they are large enough, they drop. Sometimes you will also observe that the droplets, they get large enough, but after some time when you look at it, it would have evaporated, leaving the salts behind. Because the time taken is so much, it would have evaporated from there itself. And from that basic principle lies the understanding of the depositional features. Understand how. Yes, the layers of cements, they are bulging in those areas. Wooler Lake is a fault lake. It's created on a fault line, Ilyas. Wooler Lake that you see, it is a fault lake. A fault line is there and a crack is there. That is where water, fresh water has come in. That is what is Wooler Lake. So here observe, initially, drop by drop, it will start to get bigger. And let's suppose it evaporates from that region. Now, when it evaporates from that region, so whenever water is coming down and seeping down all these rocks, all the rocks which are made up of calcium carbonate, let's suppose, and other materials. So this water which is seeping through here, it would have calcium and other materials. So when the water evaporates, it leaves behind that calcium. Now, next time, when another droplet is getting created, it will get created somewhere here. Maybe it falls on the ground. But it might also happen that a large bulge of a drop is created and it evaporates in the process. So what happens? Calcium gets left behind. Calcium is a building material, it sticks. Next time, another droplet is getting created. It might drop to the ground, it might evaporate, leaving the calcium behind, and calcium will continue to stick. So in this process, what happens? Slowly and steadily, over a period of hundreds and thousands of years, you have a kind of an overhanging structure of calcium suspended from the roof of the caves. It appears as if ice is suspended, and that is what we refer to as stalactites. Now, the opposite of it is also something which can happen and which does happen. If ever you have noticed, let's suppose, in whichever old building that you have been to ever, that wherever there is a lot of seepage on the ceiling, you will find that the floor starts getting discolored immediately below it. It is not as if the floor will remain impervious to it. The floor, because eventually all those materials, they are falling on the floor, the water is getting evaporated and leaving the materials behind, so the floor gets decolored. Now in this case also, let's suppose a drop develops like this, and that drop falls on the ground. Now as it falls on the ground, there will be that water along with the calcium, etc., which is present. Water will evaporate, leaving the calcium behind. Now the next drop which will fall will drop there itself, leave the calcium behind, get evaporated. It will build up, the calcium will build up, it is sticky in nature. Again, this process will be repeated. A continuous repetition of this process creates a standing structure protruding from the ground of the cave, and that is what is referred to as stalagmite. Oftentimes, in certain cases, you can have a situation where the stalactite and the stalagmite, they get together and they form a kind of a column or a pillar like structure. So that is when the stalactites and the stalagmites get together, that is what is formed as a pillar. So all these, they are formed in the underground region purely by the chemical action. The water is able to dissolve these materials chemically within the soil or within itself, and the water evaporates, leaving these materials. Okay, so that is what you have as the formation of this. That is what is referred to as karst topography. Okay, so why karst topography? Because for the first time it was observed in the region of Karst, in the erstwhile area of Yugoslavia. So that is where you had the observance or the discovery of it happened there. So that is why it is referred to as karst topography. Okay. Now we come to one of the most massive forces in terms of the agent of nature. We have talked about it very briefly when we talked about the continental drift theory, that glaciers are very, very massive structures. And these glaciers, they exert a weight of millions of tons on the ground surface upon which they are moving. Now, when they are moving over a particular region, that is where they will exert a lot of weight, as a result of which they will be able to erode the substance due to the weight, erode the rocks ever so slowly due to the weight imposed, and eventually the glacier might carry it out somewhere else and deposit it somewhere else. Just to give you a brief idea about how massive these glaciers are, observe, this is the glacier coming down the famous peak of Mount Everest. It is at the base of the Everest base camp, very close to it. This is the Khumbu Glacier, right? What is also referred to as the Khumbu Ice Fall. It is regarded as one of the most dangerous places to climb in your entire summit of Mount Everest, other than the death zone. This is one of the most dangerous places to climb. Now, if you zoom in into any particular area like this, a small area, this is what it looks like. So look at the size of the adult grown individuals. All this ice that you see, it is moving, but it is moving ever so slowly. So this ice might be moving at a speed of, let's say, 1 centimeter per month, or even slower than that. And the height of this ice block that you see is around 3-storied, 4-storied, 5-storied buildings high. And it is ever so slowly moving. That for you is the power of a glacier. So that glacier has got an immense weight exerted on the ground surface. That is where, as it crushes against the ground surface, it creates a variety of landforms. So when we talk about the glacial landforms, you have cirques, horns, arêtes, depositional landforms, moraines, eskers, plains, drumlins. Okay? All of these are created by the glaciers. Let us take a look at them. This will happen only in CaCO3, else it may happen in some other chemical compounds. Yes. Depending upon whichever rock material is completely soluble in water. In those regions you can have this, but generally calcium is the most soluble material in terms of the rocky materials. That is why you will find that in limestone regions primarily, where that calcium has been elaborated, or that calcium has been dissolved. Okay, so that is where you have these glacial landforms. So here, when we talk about it, observe here, this is the glacial movement. Now, here also, the same principle will be followed. That is, carrying capacity is proportional to the speed. So if the speed is high, carrying capacity will be high. Now, in the case of the glaciers, again here also, just like the case of the rivers, the speed will be very slow on the sides. Depositions will happen. Now, because this is mass of ice moving, it will not always move at the same speed. So here, observe, there are deposits happening in between as well. Deposits happening at the central portion as well. These deposits carried out by the glacier, that is what is referred to as moraines. That is what is regarded as moraines. Okay, so let us take a look at these glacial deposits. And when you take a look at the glacial deposits, you will never get confused that whether any other agent of nature has created it, because it is so humongous and so apparent that no other force of nature can end up creating this. For example, take the case of cirques. Now observe, you take a look at this particular mountainous area. It appears as if somebody has scooped up the side of the mountain from all this area. It appears as if, just like an ice cream, somebody has scooped it up. So imagine at one point of time, glaciers would have been moving from this particular entirety of region. They would have come down this area where you find a small glacial lake which is left, and they would have drained down the slopes. They would have moved down the slopes ever so slowly. So cirques are basically large amphitheater shaped erosional features created when the glaciers would move from the sides of the mountains, eroding these mountainous walls. Now, for a brief moment, have an imagination also that what would have been the situation if, rather than only from one side, the glacier would have moved from the other side also. Imagine that you would have two sides of the mountains having those glaciers, what would be the consequence? From that side also the glacier would have eroded it. From this side also the glacier would have eroded the mountain, isn't it? Because the glacier is eroding the mountain in this method. So if a situation is found where the glaciers eroded from both sides, you are left with a kind of two-sided erosional feature with a very narrow ridge-like top. This is what is referred to as an arête. Okay, this is what is referred to as an arête. And then imagine if you have a large mountain peak like, let's say, Nanda Devi. Now, Nanda Devi has got glaciers originating from all sides. Now, hundreds of years, thousands of years, millions of years later, let's say 100 million years later, eventually the glacier will manage to erode all sides, leaving behind an isolated peak-like structure. That isolated peak-like structure which is left as the glacier has eroded it from all sides, that is what is referred to as a horn. All these cirques, arêtes, horns, you will find in large numbers, large quantities in the region of Europe, particularly in the Alpine mountain range in the Alps, because there the erosion has been happening from a long period of time. And during the last ice age, many of the portions of Europe, they came under ice, and then it was melted, leaving behind the glacial landforms. Now we are able to look at those glacial landforms. Okay? Arête Shashi is basically when you have the erosion carried out from both sides. Yes, Shalu, we can say that. Vivek, thickness of arête. So this thickness you are talking about, it is few meters, few feet in general. Okay? Horn, Rahul, is when you have the erosion carried out from all sides, leaving behind an isolated peak-like format. Okay? So that is where we'll restrict the session here today. And let us take a few questions then. Okay, let us take a few questions in that case. Okay, so I'll launch a poll, and this is very simple. So we'll start with the simple question itself. Cirques arête form. Uh, don't worry, Ashwant. Whenever see, get into the habit of writing. Writing habit is much more needed. Shalu, your question that why is it that the speed is least or okay, here the answer is correct. Why the speed is very less on the sides is basically that is because that as the flow is there, it is on the sides where you experience maximum friction. That is where even in the case of the river movement, the speed is slowest at the sides. Okay. Alluvial fans, Ilias, they are formed at the base of the mountain as the river is carrying large chunks of boulders, rocks, etc. They are dropped at the base immediately as the river moves through a flat plain. That is why all those deposits, they create alluvial fan. How to remember all these details? By revision. As much as you revise, better it will be. Now, variations in the length of daytime and nighttime from season to season are due to, that is, the day length and the night length, they are variable. Why does that happen? Okay. Smriti, just as of now, just observe what is done in the class. Take a look at the additional reading materials, more than sufficient. Yes, Divyanshu, both can be found in the same river. Ashish, see, wherever a kind of a summarization can be done, I will provide a summarization. There is no harm in that. But in these areas, when you have already the entire portion in a kind of a listed format, summarization doesn't make sense overall. So if you want me to write that, okay, rivers, they create this erosional, this depositional feature, that is also already there in the listed format. So is that something that you want me to do? That write the exact same thing again, or is it something else that you were asking? So here, majority of you have given the correct answer. So why is it that there is a variation in terms of length of daytime and nighttime? Because different hemispheres, they get a different level of exposure to the sun. For example, when the northern hemisphere is tilted towards the sun, we have a longer day. When the southern hemisphere is tilted away from the sun, it has got a shorter day. So revolution of Earth on a tilted axis, excuse me, revolution of Earth on a tilted axis can give rise to variation in length of daytime and nighttime. Okay. And Saurav, this is the kind of question which can be asked from here. We have already here in this landform format, you can also get a kind of a match the following kind of a question. And here you have certain mains type question which you can try, the previous year questions which you can try writing on your own. Explain the formation of thousands of islands in Indonesian and Philippine archipelago. 10 marks, 150 words. So that is something that we have already seen earlier in the portion of plate tectonics. Why is it that you have island formation? How is it that you have island formation? Island formation occurs due to beautiful Chaitanya. Very good. Oceanic convergence. Whenever you have oceanic convergence, molten materials, they rise up as volcanic format and volcanic landform, and when that volcanic landform creates or comes above the level of seawater, it forms an island. Okay, so that is basically the reason. So in this, the introduction that you have to write about the fact that the region of Indonesia and Philippines, that consists of large number of islands. So archipelago basically refers to a group of islands. Group of islands is referred to archipelago. Now in the region of Indonesia and Philippines, you have a convergence, oceanic convergence. On one side you have the Caroline and the Philippine plate and the Pacific plate. The other side you have the oceanic crust of the Indian plate that is subducting. So that is where you have the island formation. So in the introduction, the region of Indonesia and Philippines are marked or dotted by hundreds and thousands of islands, many of them having a volcanic origin. The formation of these islands can be explained with the help of plate tectonics. That is your introduction. In the body format, you start writing that draw the rough map. Map is very much a requirement. A rough map, okay, a very rough map you draw indicating the plates. Then a sketch has to be drawn that what happens in oceanic convergence. After that you start writing that here you have these plates which are undergoing convergence, and that leads to write about the process, and your work is done. Okay. Then, why are the world's fold mountain systems located along the margins of continents? Bring out the association between global distribution of fold mountains and earthquakes and volcanoes. So, this is a question that we can discuss tomorrow, but generally, fold mountain systems across the margin of the continents, which are we talking about? Here we are talking about Rockies, Andes, Cascade Ranges, Atlas, Appalachians. Here we don't consider Himalayas and Alps, because Himalayas, they are not at the boundary of a continent, not at the margin of a continent. Okay, so take the example of these cases. Now here, when you write it out, write about that why these mountains are formed. So Invariably, all these mountains are formed as a result of convergence, ocean continental convergence. Then you can also write that you have other set of fold mountains like Alps, Ural, Mount or Himalayas. They are also created due to the convergence of continents and continents. Okay, very briefly, you can show an image of sorts, and that would be sufficient for the first part. Then comes the second part. In the second part, you are required to draw the rough map again. And across the rough map, indicate these areas of fold mountains. I had given to you the map pointing required for the fold mountains. There, talk about it, where you have earthquakes, where you have volcanoes, and why is that. Okay? That is all that needs to be written here. You have a couple of more questions. That is something that we have discussed already. For example, geophysical characteristic of circum-Pacific zone. This is a question which is repeated many times in the exam. So here you have to talk about, for example, that why is it that there is earthquakes and volcanoes across the Pacific ring of fire. So you have convergence. Which kind of convergence? Ocean, ocean, and ocean continent. Exemplify it where you have ocean, ocean, and where you have ocean continent. And this is again a 10 marker question that you have to write. Then define mantle plumes. The definition of it is given in the PPT itself. Explain its role in plate tectonics. So mantle plumes can give rise to convection current inside. Convection current, when they are given rise to, the plates will be moving away from each other, but simultaneously they will be colliding with other ones. They can be moving parallel to each other. So that is how they can give rise to plate movement. So try writing these answers. I have given you basically one, two, three, and four. Four of these answers you can try writing. Okay. Now, a few questions I'll take before ending the session. How is it possible for glaciers to melt? Glaciers to maintain ice and melt at the same time. So the glaciers will always melt at a lower height, what is referred to as a snow line. So only after that will the glaciers start melting. It is not as if where the glaciers are originating, there only it will melt. So it comes down the slope. Now, as the glacier moves down, it exerts heavy weight on the lower regions. Now, due to that heavy weight, the lower regions, they experience that heat and they start liquefying, forming a kind of a liquid flow of water underneath these glaciers. Okay. Rahul, that exact classification of the optional areas that will come slowly. Okay. The optional areas that how many people from geography have qualified, that will come slowly, but significant portions or significant number of students who had taken geography, they are as of now giving positive responses. Let us wait for the final aspect, the final conclusion. Caves are formed as a result of the chemical dissolution of the materials present in the rocks. As long as it is soluble in water, the material will be dissolved continuously. Eventually, water will drain out from some opening somewhere, leaving a large orifice underground that is referred to as cave. Okay. Alok, diagrams have to be drawn. Even if a rough diagram has to be drawn, draw the diagram. Harini, do one thing. Send your, first of all, send it for evaluation at IAS Live. After it has been evaluated, send it over, and you have my mail ID. Send over your answers to my mail ID. I will take a look and I will provide you the feedback associated. I'm not the one who will give you the marks for it, because I believe in a certain fact that right now you should not be concerned about the marks. You should be concerned about the feedback, where to improve. Send it over. I will provide it to you. Yes, you can leave. The session is over. Okay. And Anjali, alluvial fans, they are basically created immediately at the base of the foothills of the mountains. When the rivers are carrying large loads, they get deposited immediately at the bottom. That is when you have large alluvial fans. Akshay, in 2018 prelims, they asked the eruption of Barren volcano happened in 1991. So whether we need to know all the active volcanoes and when it erupted last time. Absolutely not. In 2018, this question was asked because Barren Islands erupted in 2017. That is why it was a part of the current affairs for the year 2018. And that is why UPSC had framed a question that Barren Islands last erupted in 1991 and mentioned it in the statement itself and has not erupted ever since. It was to check whether the candidates are aware that in India, Barren Islands has erupted in 2017. So that is why this question was framed. Never chase those factual questions. And this is based on current affairs and logic. Okay, so try to understand that. Yes, Kiritika, you can write that. Only this answer that you have to write, this is for 15 marks, 250 words. Yes, Ashish, that is a good score. Deepak, we'll start climatology tomorrow. Tomorrow we'll get it done and we will start climatology. Pooja, if you are appearing for prelims this time, then I don't think it is the time to give for me to give you any tips because the exam is almost on our head. So just revise. If you are appearing for it, revise as much as you can and revise the mistakes that you have committed in your test series. Revise that. As of now, just revision should be done, nothing else. From at least 1 month before the prelims, only revision should be carried out. Tajinder, exam notes of each and every topic should be written in single sheet. Absolutely, yes. Do we have to draw the full world map to show the full mountains? Yes, you have to, Nisarg. So that is where we'll end the session here today, guys. We meet again tomorrow. That is where we'll continue. And tomorrow we will initiate the portion of the discussion of climatology. And that is where we lay the beginnings or the foundation of a new beginning, so to say, for the almost the most important area in the entirety of geography. So thank you for being so patient. See you again tomorrow. Take care of yourself. Goodbye. Thank you.